No, it's not.
It's showing this.
Yeah, but the sound work, but the camera don't.
Maybe we can just shoot it off again and start it again.
This is what I did not that long ago.
Mm-hmm.
Maybe can we try with the other camera? It seems to work better. Okay, I will stop the. Cannot we turn? Wait, Bo. Can we turn? No, it's blocked again, the image. Maybe the computer is not okay. Yeah, but it's not broadcasting. I know where it is. Nice to know. I mean, I don't need to tell my computer. You have your own computer.
I'm just going to. I'm just going to talk. I won't say.
Okay, yeah, but just to then maybe I can turn off the. Yeah, Just for information, we are trying to have live record because my family will not come. So don't do anything too silly because people will see it. Hello? Yeah, it's okay. I guess it's how loud you're speaking. It's an option. Please on my hand.
No, I don't know if we made them. Should follow as a local file so in the lecture.
Maybe I can say, for information, I got a lot of people saying that it's a nice cover. It's not me who did it. I wanted to precise. I have commented. Quite boring. Hopefully.
I think that book is wrong.
Yeah,
What is it on your computer?
it's 15.
Yes, and it's 16. This is the local time in this lecture room, which is always set a little after, so that in case the students come late. Okay, it's time to start. Good morning, ladies and gentlemen, and welcome to today's disputation. Delphine will defend his thesis entitled Photonic crystals and photocatalysis, study of titania inverse opals. And this is now put forward in partial fulfillment of the requirements for the degree of Doctor of Philosophy in Engineering Science with specialization in solid-state physics, and it will now be publicly examined. My name is Gunnar Niklasson. I am professor in solid-state physics here at Uppsala University and will be the chairman during this disputation. I would now first like to welcome the faculty opponent, Professor Martin Pemble from the University of Cork, who will examine this thesis. And secondly, I would like to welcome the members of the examination committee. We have three members: Professor Vadim Kessler from the Swedish Agricultural University here in Uppsala, Professor Katja Gallo from the Royal Institute of Technology in Stockholm, and docent Sergej Valyuk from Linköping University. And it's the examination committee who will decide the grade of the thesis, whether it will fail or pass. I would also like to introduce the main supervisor, Professor Lars Österlund, here. And I think these are the people I should introduce here to the audience. And before we start, for those not familiar with the procedure, I would like to give a short summary. And first, I will give the word to Delphine to ask if she has any announcement, like a data sheet or so to do. After that, the opponent will give a brief introduction to the field of research, like maybe 10-15 minutes. After that, the respondent will describe the most important findings in the thesis for maybe 30 minutes or a little more. After that follows the discussion between the opponent and the respondent, with the opponent asking questions and offering his views on the science in the thesis, and the respondent defending her dissertation and answering the questions raised by the opponent. After that, I will turn to each of the members on the examination committee and ask if you have further questions to ask the respondent. And after that, I will invite questions from the audience. And after that, the public part of this act is finished, and the examination board will meet to grade the thesis, and the rest of you can go to the Ångström laboratory, room 4312, I think that's in our coffee room. Yeah, the coffee room 4312 at the Ångström laboratory to wait for the decision of the examination committee. And then I would ask Delphine, do you have any announcement to do before the defense starts?
Well, I must say that there might be a lot more errors, but the only one I have noticed recently, it's on page 74, on the figure 4.12. There is actually two errors. One is the detector for the infrared is not the one I'm using. There is two detectors and I choose the wrong one, at least for this schema. And also I write that I use IM0 and IM1.5 filters, but it's a name that the manufacturer gives them, but these two filters combined make the IM1.5. So maybe it's a bit confusing, right? That's basically they, I guess, a lot more.
Okay, thank you. And then Professor Campbell will now make an introduction to the subject. Please.
Thank you very much. Afternoon, everybody. So you will see that the title of the thesis is Photonic Crystals and Photocatalysis. So this can be considered as a combination of two entirely separate areas of research here. So there are people that work on just photonic crystals, and there are other people that work on photocatalysis. So in a sense, the novelty of the research is to try to bring the two together. Now, I think Delphine might describe some of these things, but I think my job is to try and put it into context in terms that everybody in the room can understand. So apologies if I try and simplify things too much. Photonic crystals, what are these? Well, these are interesting materials that are found in nature. And some of you might have seen that there are some examples which may be shown during Delphine's talk. And they can also be manufactured in the lab. Really, I suppose, why we're interested in these materials is because they demonstrate some neat optical physics. So these are examples of materials which are said to have structural color. Their colors arise not from traditional ways in which we generate colors. So for example, sitting in the middle there, your t-shirt looks green, and if I walk around, it still looks green, no matter what angle I look at it. If your t-shirt was covered with a structural color material, it would change color depending on the angle at which I view it, because it's not due to the colors that are absorbed from white light, leaving behind some colors reflected back at you, which is what you see. It's due to the nature of the material itself. And of course, this is fun to explore, and lots of people just look at it for this purpose. But underlying this, there is, if you like, some slightly more fundamental issues as to why people would look at photonic crystals. What you see with a structural color material is the ability of the material to manipulate light. It slows it down, and it can send it in directions that you wouldn't otherwise expect. So you have the ability to move light around and point it in directions that could be quite useful. So to give you a few examples of why you might try to make these things in relation to devices that we should all be familiar with, we take solar cells, for example, solar power. Why would you want to use a photonic crystal in a solar power environment? Well, the photonic crystal has the ability to capture the light that falls on the surface, and in some cases it has the ability to confine the light in the structure. And that means that the light has more time to be absorbed by the solar cell, and so you could improve the efficiency of the solar cell that way. Another crazy example that I often tell my students about is where you might have a device that gives out light, like an LED or a laser. It's possible to take the surface of a laser, if you like, where light would come out. It's usually an edge, but let's just imagine it as a surface, and the light will come out in this direction. It comes out of the structure because this particular surface it's mirror-like, but it's not a brilliant mirror, so there are losses, and you see the light coming out. Now, if you put a photonic crystal on top, it's like you provide a gateway which helps the light to escape from the structure. So bizarrely, covering the surface with a layer of this material can actually cause more light to come out of the material. And if you can understand that, then you understand what a photonic crystal actually does. So apart from solar cells, where we might use light confinement, there are examples of other kinds of devices that all which would use these properties associated with the structural color. One of the latest examples that people are looking at would be how to replace electrical connections inside computers and processors. Okay, now, if you imagine the connections that take place right down at the transistor level, okay, light's not really going to help us very much there because of the wavelengths that are involved. But jump up a few levels in terms of the architecture, and there you can find that you might get light being able to be transferred from chip to chip in the processor, or even from board to board in a stack of these things that you might get. And this is an area now which is attracting a lot of attention, because it's a way of essentially cutting down the amount of power that the computers would use. You know, we all have amazingly powerful computers in our pockets now with cell phones. And some crazy figure like 25% of the Earth's power consumption is based on some sort of PC and related device, including cell phones and stuff. So there's a big need really to try to limit the kind of power consumption. Okay, so that's photonic crystals. I'm sure Delphine will say a bit more about this. And then you have photocatalysis. Okay, so this is a combination of two words, if you like, photo and catalysis. So it implies some kind of catalytic reaction which is produced by light. Okay? Now this happens all the time in nature, but we also can use this effect in various kinds of devices. One of the simplest devices that uses photocatalysis might be a window. You might think to yourself, well, how do you use photocatalysis in a window? Well, it's possible to buy window glass that cleans itself. Okay? How does this work? Well, it contains a coating of a material which forms one of the main planks of the work that we're going to hear about this afternoon, titanium dioxide, which is very good from 2 points of view if you happen to be interested in making good windows. First of all, it's very, very tough, and it will stay on your window for 20, 30 years or so without disappearing. Okay, so it's chemically very, very stable. But the second thing is, if there's a little bit of ultraviolet light falling on the window from the sun, then something strange happens. The surface becomes active towards organic material that might get trapped on the surface. And it's more than just active, it undergoes a catalytic reaction, so the surface provides, if you like, a route by which it facilitates the chemistry to take place. And this reaction destroys organic material completely. So in Delphine's thesis, one of the molecules that she's used to test the photocatalytic activity of her titanium dioxide is a molecule called stearic acid, which is a greasy, thick organic molecule that does a really good job at simulating dirt. Okay? And when this is placed on a titanium surface like a window, and the sun comes out, then very, very quickly chemistry takes place and the bond between the window glass and the dirt is broken very quickly. Now, if you happen to have a little bit of rain as well, so this process was developed for windows in the UK by Pilkington Glass, although it's also been picked up by a number of other companies. And the UK is not known for having high levels of sunshine, particularly ultraviolet, but actually there's enough ultraviolet to make the glass turn on and work. The other thing that the UK climate has is lots of rain, and that turns out to be also good. Who can tell me what happens if you wax your car and then you put some water on it with a hose pipe? What happens to the water on the surface? It beads, it forms beads. In other words, the water doesn't want to touch the surface. It's shying away from the surface. The surface is said to become hydrophobic, water-hating. Something strange happens with titanium dioxide when you shine ultraviolet light on it. It does the opposite. The surface becomes water-loving or hydrophilic. So here's my window. The sun is shining and there's some dirt. The dirt is weakened in contact with the surface by this photocatalytic reaction, and then it rains and the water streams down the window. Not forms drops, but it flows down the window and it washes away the dirt. So this dual effect is what gives rise to the self-cleaning effect of the windows coated with titanium dioxide. In fact, the company that developed this process used a very bizarre test to see how effective it would be. They thought, what would be the worst thing that you could get to stick on your window? And it turned out to be a bird poo. Yes, they developed a bird poo test to test the window. And although bird poo contains a lot of things that aren't organic, the stuff that holds it onto the window, the glue, is organic. And that's why it works, because that's destroyed. But anyway, back to the thesis. So now we have two areas of science, photonic crystals and photocatalysis. both of which have been studied extensively. What Delphine has tried to do in this work is to combine the two, to see if the light manipulating properties that are exhibited by photonic crystals can be used to enhance the photocatalytic properties of titania when the two types of materials are combined. And we'll hear a lot more about that this afternoon. Okay. Thank you.
And then the summary of results.
I am not the professor, so I
Yes. Yep.
Do you see enough? Yes. Okay, I will try to be brief and clear. Hopefully. I think you already know the title of the thesis. I just say that I had added the MISAO. Might feel a bit strange, but it's because there is really a lot of Delphine Lebrun who are doing science. So I wanted to have, I don't have a middle name, so I just added something very exotic. It will be very simple. I just describe very fast all these, the ideas that Martin have already told you about. And then I will just give you some results on the fabrication of photonic crystals, on how they look, and when we observe them optically. And then some results on the photocatalysis, obviously, and then just a little bit on like my view on the thesis, basically. Well, we have explained that we have this photocatalytic effect so that you can clean windows, but you can also clean the air or the water. And I think you already know that like cars and industry and I think everything, plastics, everything we produce a lot of chemicals in the air, and you want to get rid of them. And the idea is that you want to get rid of them because they have health and environmental problem that they cause, but you don't want to put energy into it because making energy always pollute. So then what you want to use is to use the solar energy because it's free. Now here you see what we call the irradiance. That just means how much light arrive on the surface of Earth, and you have the black one is on the top of the atmosphere, and then the blue one is like mostly at the sea level. And you see that this is the visible, so this is what we can see. Infrared is all like the vibrational of molecules and heat and stuff like that. And UV is what gives you skin cancer, basically. So it's higher in energy. And you see that what is most is around 500 nanometer. And in ideal world, you will want to use this light because it's where you have the most of it. Unfortunately, titanium dioxide absorbs just here in the UV. So we want to enhance this UV absorption using the photonic crystal because we don't have that much UV arriving on the sea level. How does that work? Well, this one is very simplifying things, and it's like solid state physics things. Basically, you can imagine that you have a photon arriving on, let's say, a particle that's what we call a semiconductor, which means that it have kind of a gap in energy, and it will forbid some electron to pass. So you cannot pass electricity easily into these materials. But if you absorb some light, you can give energy to an electron, and it will jump to a higher level. It will be excited. And if you are lucky, you can separate these excitations, and even more lucky, you arrive at the surface of your material, then you can give this excitation to molecules that are absorbed on the surface. So you make, this is how it works, the photocatalytic effect. So you absorb a photon, it creates an excitation, and this excitation is transferred and break bonds, for instance. What is interesting with titanium dioxide, so here, the material I use, is that it's what we call the oxidation power, so how well it is situated in energy relatively to other materials. For instance, here it's just rust, like zinc oxide, but mostly regarding this is some how do you call it? It's like when you want to transform a material to another. And what is important for titanium dioxide is the water and oxygen. So we can, titanium dioxide can give, it has more energy than the blue lines here. So it can give electrons, and it is below, so it can also receive electrons. So it's how you get all of this process forming. So you get a lot of this highly reactive species, because this is very simple molecules, and when you try to break them, they don't really like it. And then they tend to react with anything on the surface. Well, we got the example of the windows. There is also possibilities now to, there is really a lot of application, but what is interesting, for instance, is this company, Italian company, Italcementi, and they put titanium dioxide in concrete. And they don't give the formula, of course, but they managed to have the same. If you eliminate these dirty tiles, you can remove the dirt with just elimination, so you don't need to clean your buildings as often as before, like from pollutions. Okay? So now, that was very quick stuff. So now I will just speak very fast on the natural photonic crystals. And then what I call artificial is the photonic crystal that I fabricated, and then I will show you some optical study. The optical study was very thorough, so there is not everything from the thesis. It will take too long. Like we explained, a photonic crystal can be found in nature. The most famous ones are opal, and we say that they have a play of colors. And that means that when you take them in your hands and you change the angle of view, you will see different colors flashing, all in the visible. Here is butterfly, is one that is here. It's called morphoephemer, and it's from Brazil. And it's the same, when you change the angle, you see it becoming sort of green to like this turquoise blue. If you observe this under a powerful microscope, so scanning electron microscope, you observe a very regular structure like that, and these distances are close to the distance, the wavelengths of the visible. So now you can understand that these photonic crystals work very well like that. That you have a material, and it's periodically spaced and repeated pattern. And an example I really like is this chameleon. So it's a study from 2015. They have this tiger chameleon, I think it's called, or something like that. And it can change from green to red, it becomes excited, so it gets red. And they wanted to understand how it did it. And basically, when they observe the skin of the chameleon under the scanning electron microscope, they see this little, well, here it's dark, but it's like little blob, and they call them guanine nanocrystals, so they are very small, and they are periodically put and periodically spaced. And they see that when it's excited, this periodicity is changed. So this is how, now you can have an idea that when you change the periodicity here, you change the color that is reflected. So this is what we can understand here. If we change the angle, we will change the periodicity at which we see the different little steps. Oops, sorry. So now, very fast, I just want to say that if you have a material, let's say that you observe it, it's just a normal material without periodicity. If you observe it with some spectrophotometer, so you have in transmission, it just have a bit of absorption and then have a bit of reflection. Now, if you take the same material, but you order it with this periodicity, then you will observe what we call, well, what I call a dip in transmission, or you get a peak in reflection. So this is the term, this show you that what you see with your eyes is what is reflected by the object you are looking at. So this peak in reflection give you this vibrant color, these vibrant colors. And there is a very simple mathematical expression that you can use to have an idea of which type of color will be reflected, depending on the periodicity, which is the D, and then the type of material, which is the little n, which is what we call the refractive index. And the refractive index is fixed, well, at least for some material is fixed in the visible, and what is F here is the filling factor, so it's how much of the material you have. So if you change the periodicity or the material or how much you have of each material, you will change which color is reflected. So to do my my samples, I first made a template with polystyrene, so just these plastic beads, and they are between 160 nanometer in diameter to 500 nanometer, but I mostly use 200. And the deposition is very simple. It's like cooking in the kitchen. You just take the concentration of your polystyrene, you put it in water, put it in the oven, let it rest for at least 12 hours, and then you obtain this, what we call FCC, phase cubic centered structure, which is just a very close packing of balls on top of one another. Then I'm not really interested in polystyrene. Polystyrene doesn't do anything, it's not photocatalytic. So what I want is to have my material, titanium dioxide, on top of the polystyrene. So I use atomic layer deposition, I will explain very soon how it works, to deposit the material on top of the polystyrene. Then I use a technique called ion milling, which is just sending iron really fast on the surface, and it will open up here. And then I can remove the polystyrene. I just put them in the oven again, and the polystyrene evaporates. So then then people have called this inverted structure, so inverse opal. I hope you follow this one. Very fast on this deposition technique. What is interesting with AMD is that you have, this is like a chamber, and you have the oven. Then you have two sets, or at least two sets of chemicals, and you will introduce one chemical that will deposit everywhere. Then you wait a bit, you remove the chemical that is left in the chamber, and you introduce a second chemical. The second chemical will react with the first chemical, and then you will get this deposition. So for instance, with titanium dioxide, it's called TeCl4 and water. So you introduce them one at a time, and they will react when they are attached on the surface. So it's very conformal. So there is people, for instance, who have deposited material on one of these butterflies' wings, and they were able to remove the wing and have the inverted structure. Yeah, that's basically it. And then you have these cycles. So normally you're supposed to deposit one monolayer at a time, but it's never working. This is the ideal world. Just to point out, something that is interesting with this inverted structure is that since the polystyrene are touching each other, you cannot put the material where they are touching. That's why the gas cannot go in there. So when you remove this polystyrene, at the place of the neck, you end up with holes. So that means your wall structure is connected from the top to the bottom. I think this is what is very interesting with inverse opal, because It's a sponge is very nice because it has a lot of surface, a lot of holes, and you can circulate. But in the inverse opal, they are all connected. So how does it look on the scanning electron microscope? Well, it looks like that. So this is an inverse opal of alumina, aluminum oxide. And you see when you have a close-up that you have these holes that show the communication. And we have here like maybe halfway or something like that. This one is some X-ray diffraction, and it's just to show that once I've deposited this titanium dioxide, I bake it, and I obtain these peaks represent the crystalline form anatase. So it was just to verify that I indeed have anatase form on my samples. So there is two types of samples. There is sample where I deposited directly titanium dioxide on the polystyrene. So it's titanium dioxide inverse opal. And then I have some sample where I deposited alumina first, and then titania after inversion. So I have alumina titania inverse opal. Now for the optical study. This is for the polystyrene opal. So they are still a photonic crystal. It's just that they don't have any photocatalytic activity, so they don't really interest me per se. But here you have on the left you have the transmission, and on the right the reflection, and you can see that they don't have much. You have the diffuse, specular, and total. So the diffuse and specular give you the total. You can see that we have this peak in reflection, so it's close to 500 here. And we have this dip in transmission, as I showed you before. So this is how I characterize my samples. I take the position here. This is what we call the photonic band gap position in the middle. And then what we call here full width at half maximum, sorry, FWHM. It's the middle here, so the width of the photonic band gap. And then you can use it in literature. There are some people who have made this like definition to be able to compare their sample from theory to practice. So this PBE is just basically you divide this width by the position here. And theoretically, for the polystyrene opal, it's close to 0.1. And for all my sample, and maybe it's a bit confusing here, but this is a theoretical one, okay? This is the value of the PBE, so this full width divided by the position, and then this is the number of layers. So how many beads of polystyrene I have on top of one another. And in black is what is extracted from the reflection data, and the blue square are from the transmission data. As you can see, a lot of them are a bit below the theoretical one, and maybe some of them above. And that just means that my samples were not perfect, which is not so surprising. I mean, it's just putting them in the oven, it's not much control. And you see that there is here, when it's above 70 layers, the transmission have like a huge increase that look very well. And we have this increase in almost all the characteristics. And we think that there is a lot of diffusion arriving, so a lot of scattering that create this increase. So that basically we should use the reflection data as the base for analyzing the photonic crystal, not the transmission. The transmission is a bit fishy, we say. So now we can go to the two different inverse opal I created, the alumina titania and the titania inverse opal, so left and right. And you see that I put the reflection data. So for instance, here I have the polystyrene. Then I deposited titania. Then I have done some ion milling to remove a bit of the layer. Then I have baked the sample, removing the polystyrene, and up, I got this titania inverse opal, and it has a peak in reflection. And it's something similar here for the alumina titania. It's just that it's polystyrene, polystyrene, alumina, alumina inverse opal, titania, alumina, titania inverse opal. So you see that we keep these peaks between from the templating to the final product. The overall two spectra, they are the spectra of the last product. So here, titania inverse opal, and here, alumina, titania inverse opal. And you see the transmission total and the reflection total. So you see the peak in reflection. You don't really see the dip in transmission because titania start to absorb somewhere here. And you see here the absorbance. So it just, for here it will be 100 minus this one plus this one. And you see that for both of them, we have a slight peak here. And this is an increase of absorption from the fact that we have a photonic crystal. Because titania just absorbs here, it does not absorb in this range. Just very fast mentioning I made some theoretical calculation using this very simple math. So it's not very precise, but it shows an idea of what's going on. And for instance, this is a calculation for alumina inverse opal. So just alumina inverse opal, and you change the alumina thickness, and you get this position of the photonic band gap. And then what I did is that I changed what we call the shrinkage, because when you bake a structure, it will contract. So you get a shrinkage, and it's predicted that the shrinkage increases. You change this photonic band gap position a lot with shrinkage. So then, using this kind of data, I was able to get an idea of how much my structure has shrunk. And I could use different ways to do that. I could use what I call photonic band gap shift, which means I take the polystyrene peak position and the polystyrene alumina peak position, and I check the difference between them. This gives me, I can make calculation again and get an idea of which shrinkage corresponds to this shift. And I can also just take the actual position of the photonic band gap of the final structure, and also knowing the thickness, I can get which type of shrinkage I have. So then this is the experimental results here, and we have basically a trend that the shrinkage increase with the thickness. And I think this is based on the tension that the structure have on this. The thicker you have, the less place you have to move. And I guess the less elastic you become. Okay? And then, yes, so this is another last result on this alumina inverse opal. This is intermediate, but they are still interesting to study. There is yet another definition. I'm sorry about that, from the literature. This time they call it this delta lambda photonic band gap. And it's basically the periodicity divided by the position of your photonic band gap. So this is to be able to compare samples between themselves, and like with different periodicity and so on. So this is, the red line is my calculation, again using this simple Bragg-Snell law. And the red circle are experiments. So it's just showing that it's, the scale is quite large. So it's relatively, it's very simple math, but it seems to work relatively well nonetheless, at least for my sample. So now we can go to the result for the actual inverse opal that I use. So first we have so again the same definition, this periodicity divided by the position of the photonic band gap. And this is for the titania inverse opal. And in blue, dotted blue is the theoretical one. And these ones are the important one here. They are the experimental data. And again, it's like, it's not totally perfect, but it's the same. It's kind of zoom up. So it's relatively following the predicted pattern. And then, of course, there is always some uncertainty on the thickness I have deposited. For the alumina titania inverse opal, it's a bit more difficult for the prediction, at least, because you need to take into consideration not only the alumina thickness, but you have to take into consideration also the different type of shrinkage that you can have. So I made some calculation with example of what I had in my experimental data, and you see that it's the same. It's kind of follow the same trend again. Yes. Now I start going with optics, and I will go to the photocatalysis. So this is the experiment I did with my sample, which is titania inverse opal and alumina titania inverse opal. And the first one is this stearic acid degradation. This one is in air. And methylene blue degradation. This one is in water. So stearic acid, it's this long chain, carbonated chain, and it's like this oily substance. You can actually find it in nature. And I use what we call Fourier transform infrared spectroscopy. It's just basically you put your sample in the sample chamber, and then you send an infrared beam onto your sample, and you have an infrared detector. And this infrared beam will make the rate, the molecular bond. I think for this one is you mostly check the oxygen bonds for stearic acid, and you will get response from the sample, depending on what you have on your sample, of course. And you can monitor a change. For instance, if you start to degrade the material, then the number of vibrations will decrease, so your signal will decrease. So basically, it really is a basics of it. And then we use what we call an arc lamp that produces light, basically. And then you can choose to put some filters, so you can try to imitate the the type of light that arrives on the surface of Earth, or we can choose some specific band path. So I did actually both, but I will show only this solar illumination. So this is a typical example. So you get these two peaks for stearic acids that you monitor, and the top one is at the beginning. So I have put stearic acid in my sample, and then I start to measure, and I start to illuminate, and you see that the peak intensity decreases. And what you do is that you calculate the area underneath the peak to get, you can get a proportionality between the area you measure and the number of molecules you have on the surface. And what is interesting in photocatalysis is that you can take this change in area with time, and you just normalize it to the first area, and then you can monitor this decrease in time, and we obtain a linear decrease from this law, and we can obtain the slope of this decrease, and this is what we call a degradation rate constant. So normally it should stay the same for the sample. For each sample, it should be a specific one. What I did now is I plot all the results I have for all the samples I have measured. I have measured them at least twice. And what we see here is phi, not k, because I was able to calculate it. Phi is a quantum yield. It's a bit more precise than k, at least to compare samples between themselves and over people's sample. And basically, it's a degradation of molecules that you have on the surface per time, divided by the number of absorbed photons, absorbed light per time. I was able to do that because the manufacturer gives you the spectrum of the lamp. And you can see here, the dots, the black dots represent the position measured optically of this photonic band gap. So this is where the peak in the reflection is. And then these blue and red bars represent how wide this photonic band gap is. The vertical line represents the absorption edge of titania. So titania cannot absorb here, but it can absorb all of this here in the UV. And what we would expect is that samples who have a photonic band gap close to this absorption edge will do much better than, say, for instance, this one, that is very far away. That this one will increase absorption in the visible and nothing happened. So the thing is that with these results, we show that for some samples, it seems that it worked quite well. Some of them seems to have quite high efficiency in comparison to, say, some samples that are not at the right place. But then there is some samples like this one or this one, where you would expect that it would be something similar, and yet it's not. So basically, for this solar illumination, I was not able to find a clear lead to say that, okay, because I have a photonic crystal, my samples are more active. I will discuss very briefly at the conclusion what I find with the bandpass filter. So when I don't have a solar, but where I choose which type of light arrive on the sample. Then the second setup was with methylene blue degradation. So this was made by a colleague. It's a very basic setup where you have this water and you put this methylene blue solution, so it's blue, and when you get degraded, it loses its color. So what you do is that you have a red laser going through the solution, and as the methylene blue disappears from your solution, the laser intensity increases, like the measured intensity increase. So then this is what you record, and you basically let it rest like that, and you have this UV lamp. And I didn't have the spectrum of the lamp, so I was not able to calculate this quantum yield. And basically, what I understood, this methylene blue loses its color when these double bonds are broken. So this is what a typical spectra look like, results look like from this setup. And basically what you do is that you put a certain concentration. So here it's 1 ppm. And the lamp is off. So you just put the methylene blue and you measure with time, here for 500 minutes, you measure what is the absorption of the red laser in the solution. And you see that it's decreased and then it kind of gets stable. And this is because there is an absorption of the methylene blue a bit everywhere on the surface of the container and on my sample. And then you turn off on the lamp, and you see that there is a sharp decrease of the signal, so that means there is a decrease in concentration of methylene blue. And this is this part that I have analyzed. So then it's very similar to the steric acid. The same, you take the concentration with time, you divide it by the first concentration, you take the logarithm, and you plot it with time, and you get a linear expression. And the same, you obtain this degradation rate constant. So I plotted the same data again. Normally, it's also 2 measurements per sample. And so this time is a degradation rate constant. And this is, again, photonic band gap position, photonic band gap width, and absorption of titania. So you might have noticed that all of my samples seem to have shifted toward the visible. And this is because they are in water. And I have told you before that this refractive index was important. And the refractive index of air is 1, and of water is 1.3333. So that means you will shift the photonic band gap. So I have made some very few measurements on several samples that have been inside this solution of methylene blue. And I basically got that it's shift around 50 nanometer, and I made some calculation, and it's roughly shift 50 nanometer. So I shifted all my samples by 50 nanometer to plot them here. And then you see that, again, we don't get any clear picture, because, for instance, this sample is very far away from the absorption of titania, so it should not have any influence. Whereas, for instance, this sample should be better. So it's all, again, very blurry. It's like it doesn't seem to be any, at least on the type of experiment I made, I was not able to assess that there were something going on, something added by the photonic crystal. So I soon will stop talking, or a little bit at least. Just mentioning a few things that I have gathered from my thesis. Basically, this atomic layer deposition is said as something that is very precise, that you can control very easily. And it's true when you have very geometrical features and when you have like very open features. But for what I've noticed on my structure, which this closed pack structure, I have a difference of deposition depending on where the sample was in the chamber. So some of the samples were deposited in the same condition at different deposition thickness. Then just that the structure shrinkage seems to depend on the deposition thickness. And this is something that annoys me a lot in literature because a lot of people just find one sample and they go under the scanning electron microscope, they measure and they see, okay, my periodicity have changed this percentage, so I have this percentage shrinkage. And I have just shown that for my sample, this shrinkage is dependent on the thickness you have deposited. So if you're not really sure that your sample have been deposited the same thickness, then you can say that your shrinkage is this number. But I would say that it might be more interesting to check with this optical measure, because then you have a better idea what is your shrinkage. Then we have this weird thing, this increased scattering in mostly in this polystyrene opal, that it seems that there is kind of a threshold at more than 70 layers. There is something increasing, like the scattering is increasing a lot. And it would have been something linear, like it's increased with the number of layers. I would have said, okay, I can understand that. But this one is really that there seems to be this threshold, but after 70 layers, it's increased a lot. And I would be interested to know why, if someone has an idea. Then something interesting is that when you do these absorbance measurements on the inverse opal, we see that we have an absorbance on the whole photonic band gap. But then apparently for the photocatalysis, either we have not enough statistics, so I should have made more measurements, not possible with the time, but maybe like us. Or maybe there is we need some more control environments. So for instance, for the air measurements, I was not able to decide the temperature or the humidity in the chamber because it's just exposed to the whole lab. And then from these bandpass measurements I made, so when I had not the solar illumination, but a specific light illumination, I was able to show that we could see a photonic band gap effect, so an increase of photocatalytic activity, but only if the illumination and the number of layers of this steric acid, so this molecule, were the same. So basically, the effect seems to be weaker than other effects that influence the photocatalysis. So you can, the photocatalysis, you can, if you, if you change the power, so how much light you send per time on your sample, you will influence, there is some windows where you will influence the activity. And then the same, if you start to have one layer of molecule, or if you have 100 layers of molecule, you will change how the photocatalytic effect will occur. So this shows that they are stronger, the effect on this seems to be stronger than the photocatalytic effect, the photonic crystal effect. So my conclusion is that this, I'm sorry, I'm starting to be tired. This photonic crystal, there is an effect, but for my type of sample, it was on too short width. So you saw these peaks, they were like, I don't know, 50 to 70 nanometer. So this effect is on a very short bandwidth. So then my conclusion was that maybe for the photonic crystal, at least if you want to use it in photocatalysis, maybe we could use it some way else, not just to increase this titania absorption, but maybe to send back light into the structure, or maybe try to absorb some infrared light or something and use it for something else. Because it can be also used to increase the photocatalytic activity on some materials. And then something that's annoyed me a lot, I'm sorry if I sound very pompous when I say that, but from reading so many articles in photocatalysis, I want to ask why there is no standardization for this. Like in solar cells, where you can send your sample to a company and they will measure it, and then they will tell you, oh, your solar cell is that. Because in photocatalysis, everyone has his own setup, and everyone has his own definitions and his own calculations. So it's very difficult to compare your sample with someone else's sample. So I was a bit annoyed with that. And there is some people who have tried to make a standardization, but they were a bit, it was, I think, from the 90s or something, and they use a chemical that is dangerous, and that's in solution. So my sample will not have worked, because they wanted to dilute they wanted to compare their sample with Degussa, which is like a company that produces this nanoparticle of titania, and they just mix this and make a measurement and compare their sample to this mix. And I could not do it because I could not destroy my sample for that. And then I made some trial with LED illumination, and I saw that it should be possible to make some photocatalytic reaction with these LEDs. And I think we should, at least maybe the photocatalytic community should start working into it, because, I mean, hopefully soon enough we will have a lot of LED illumination a bit everywhere in those things. I mean, it's a lot better than the incandescent lamp, say. So that was basically the summary of 5 years of work.
You can stick there or in here where the truck.
Okay, so last we need to tie Delphine to the chair and shine the light in her face now.
Do you think you will hear me, or if I don't have the microphone, it's okay?
See how it goes. So I enjoyed reading the thesis. It's very entertaining, and it certainly covers a lot of material. Let me begin by asking a sort of esoteric question, really, that you can't possibly get wrong. You'll see why. What part of the work did you enjoy doing the most?
Well, let's see, because usually the part I like the most is to try to design a new setup or a new experiment, and then you start the experiment in the afternoon, and then you go home, and in the morning you're like super excited, like, did I get positive results? Most of the time it was not, but this part was the most enjoyable, I think.
Okay. So let's talk about photonic crystals, obviously as a sort of starting point. I mentioned a few applications of these things. You mentioned a few applications. Can you think of any applications of the colloidal photonic crystals that are currently sort of commercially being developed?
Of which one?
The colloidal photonic crystal, artificial opal.
Yeah, actually, as a matter of fact, I got approached 2 years ago by someone working with IKEA, and they were interested in having display of colors on like maybe, I don't know, like furniture or something like that. So that he saw it was when I did my license. It's like a middle examination that you publish in the university. And he wanted to know if in my opinion, they could use this polystyrene, for instance, this colloidal opals for decoration. And then I think I told him, I didn't heard about him again, but I told him that maybe he should use silicon oxide because they are more sturdy and with higher temperature deposition and so on. But apart that, I'm not so sure. I mean, it's very pretty.
That's right. I mean, that leads us to the very obvious one. I guess in Japan, certainly you can buy artificial opals that have been made into jewellery.
Yeah, I think so, yes.
Yeah, that's right. And there are also people in Japan who, interestingly enough, are trying to make stretchable fabric.
Yes, I have actually, when I visited, it was in your lab, no?
Yeah.
Yes, when I visited Martin's lab, it was very interesting. One researcher was trying to get these artificial opals, these colloidal opals, on fabric that could stretch. And that means that when there is vibrations or earthquake, it will change color because it starts to stretch the building.
Yeah, that's
quite cool.
That's exactly right. And, I heard last week that there's a big activity now in Japan looking at the development of these passive sensors. So you can imagine, everybody, you put these patches onto a large structure and you just watch it. You look at it as you walk past on a day-to-day basis, and if the color changes, it means the structure is under stress, as Delphine says. So obviously you focused on these photonic crystals that have been made from the polystyrene spheres, and you mentioned that you could do it with silica spheres.
Yes.
How else can you make photonic crystals?
Well, there is this PMMA.
Yeah, so with spheres, yeah.
Yeah, but then there is a lot of structure that you can do. I mean, these photonic crystals are in 3 dimensions, but you can do 1 and 2 dimension photonic crystals. And I think the first ones that were made were inverted 1-dimensional or 2-dimensional because they made it in the radio wave or something like that, and they made just hole in the plate, so regular hole in the plate. And then I think this is like all the work from Eli Avnovich and Savage John, and they have also a lot of this stock piling. So you have this kind of log. I mean, they're not log in the sense that they're not big, but in the micrometer range, and they can pile them at regular intervals.
Yeah, wood pile
piles,
structure. That's right. So these are things that the semiconductor engineers can make quite effectively. So why should we make photonic crystals out of spheres of polystyrene or silica? What's the advantage of the colloidal photonic crystal over something like a wood pile structure?
Well, I will say that you can, for the colloidals, you could really easily do it ever on the wall-to-wall structure. So you could have this, because for instance, if you apply the Langmuir blowjet method, you just make float this polystyrene or these beads, and then you apply some tension, and they will form this structure that you want, and you can just deposit them layer by layer. So you could have a roll-to-roll fabrication, which is, I think, favorized a lot by industrials. Or you could also make this, the way I do it is like make the whole structure at one time, so you could have this big incubator. I don't know for the wood pile structure if they could do it.
How do you imagine they do it if it's made by these device engineers who have to make something that looks like a pile of logs, as you say, all stacked one way, all stacked another way, all stacked the other way? How do you think that they would do that? From a device engineer perspective, what sort of approaches, not exactly how they do it, but what technologies would they use?
Let's see.
But if I told you, for example, that they start with a block of material.
I guess some kind of etching.
Exactly, etching and lithography.
Okay.
So now you have etching and lithography compared to stacking of spherical particles. What's the obvious advantage?
Well, you don't have any instruments involved, and you don't need any technical. I mean, like I say, it's really like cooking. You just cook.
I'll tell my people that you don't need technical skill.
Well,
I like that one.
I mean, you of course you need to experiment a bit to know like the right concentration, the right temperature, and so on, and the right surfaces. But
Okay, for the man in industry, what's the advantage?
well, like I say, you really don't need any instruments. So
Right,
you can
so
just let.
Consequently, the whole process is a lot
But I don't know if it's faster, but it's cheaper.
cheaper.
That's what comes.
Yeah.
But the
Very
polystyrene are not cheap if you don't make them yourself.
No, that's true. They are expensive.
So,
Make them yourself. Actually, PMMA is easy. Polystyrene is more difficult.
yeah, it's they are more the model dispersity is more difficult.
Okay. Okay, then we're on page 33. Let's just sort of jump in. And 33 and 34. Okay. Yeah, no, it's fine.
I have no idea what it is.
Yeah, so what we're doing here is we're looking at, you're making a nice comparison. You know, you can compare photonic with electronic, and there are many, many good analogies between the two, particularly in terms of the band structure. Yeah?
Mm.
So if you take it, sorry, if you flick to the next page,
Yes.
where you've got the figure there.
Yeah.
So there's a nice photonic band gap diagram. So I would call that an optical Brion zone. Yeah.
Mm.
So when you sort of said, and here you see a local photonic band gap between gamma and L. What does it actually mean between gamma and L?
Basically, this all these letters are symmetry point in the material. So because since you have a periodic structure, you can design symmetry points, and usually, at least I think it's the same for photonic crystal. The gamma point is the middle of the structure, so of the symmetry where you will start to design your symmetry, and then all these letters are on the surface. So you define this Brion zone. And what I mean is local that means it's only in one direction. So in this direction, you will get this photonic effect. So you get this reflection in this range of light. B over lambda, B is the periodicity, and lambda is the wavelength of light. Whereas when we see this, the orange zone is for all the direction in your structure. So if you turn your structure, you will get this reflection again.
Okay, so if you had to use one of those gaps as a complete reflecting mirror, which would you use?
I guess it's depends on the use actually, because I mean, you
If you
would
wanted it to be a mirror independent of angle.
yeah, then the complete photonic band gap.
But the interesting thing is, of course, it's only a mirror for a particular wavelength.
Yes.
Yes. For that particular structure. But nevertheless, you could design that into your optical component. Yeah. So you call the other one, you call it local. There's another word that's sometimes used to provoke pseudo, exactly. Pseudo gap. Very good. So pseudo gaps are actually more interesting sometimes because they imply that you can stop light moving in one direction, whereas maybe it will carry on moving in all of the other directions. Yeah. Okay. So in this section, you sort of describe how you get the photonic band gap. I think it's on page 35. You have your reflection and transmission diagram. Okay, so let me ask you a question based on something that we've seen and other people have seen as well. So okay, we maybe make a structure where we use larger spheres.
Yes.
And you plug everything, all the numbers into the Bragg-Snell equation, and you find that the stop band comes out at around about 900 nanometers. Okay?
Yes.
And sure enough, if you scan from longer wavelength down, so 1,000, 900, you see a peak, and you keep going down, and then at 450, you see another peak.
Yes.
Why do we see the other peak?
This is you have several order of reflection because if you have if you have a periodicity, let's say you have a stockpile of planes, then at some point this periodicity you will double the periodicity. So then I never see this second, for instance, second order. So that means you divide the first order by 2, and then you get. So if you get your position at 900 and you divide it by 2, you are around 450. And I never see them in my optical measurements because they are too far in the UV, and polystyrene absorbs some UV light.
Yes. I just think that it's something that might have contributed to some of the scatter that you didn't see in the results. We should always be aware that even though you can't see it, it will actually be there.
Yeah.
So it's quite interesting. People often forget second order
yes.
with these things, but you certainly know that one.
It's more. I mean, the first order is a stronger one.
Of course.
So maybe that's also why you cannot tend to dismiss it. Mostly for my polystyrene, I mean the reflection peak is never higher than say 40% or something. So I guess the second order might be 20%.
Yeah. What's the record, do you think, for getting a reflection peak from, say, some kind of artificial opal, no matter what it's made of?
I think I have seen literature with 80%. But then the thing is that I have noticed, for instance, the sample that I made at your lab, because I went to his lab to make some sample.
But importantly, they're not used in the thesis.
No. I mean, I just I made measurements with your optical setup, which is a laser, so that's shine onto a wave guided light, and I use an industrial spectrometer. So then the light is with the big. How is it in English? It illuminates the whole sample, and I think when I made the measurements in your lab, I was probing a smaller region, and with the industrial measurement that I made, with the spectrometer I measure in the millimeter squared range, and I think it changed. The thing is that the photonic crystal is very fragile to disorder, and I have, in the micrometer range, I have a good periodicity, but then when I start to increase decrease the resolution of the scanning electron microscope, I see that I have default. So I have steps, or I have missing beads, and this I think kind of makes that I have very local organization, and if you probe this local organization, you get a more refined peak, and then you get this higher effect. But for me, it's quite broad, and I have some samples with very broad peak, and then I think the reflection peak decrease.
I think that's an issue with the polymer-based samples anyway, in that they're actually very susceptible to damage in the electron microscope. You can use that to your advantage. You can actually make defects where you want them, write lines with the electron microscope beam if you so desire. But the other side of the coin is that you might not. What you see, it might not be exactly what you started with.
Yes, but I coated them. After a while, I coated them quite evenly with gold and palladium. But yes, it's not easy to observe on the microscope.
Okay, and obviously you've talked to us about the Langmuir-Blodgett method. Do you know what's different about the photonic crystals that are made by the Langmuir-Blodgett
Yes,
method?
they are in HCP. So instead of LCC, so well, I don't know. I think it was one of your articles, or maybe
Yeah, they're more disordered. They're certainly more disordered. I wouldn't go as far as to say that they're HCP.
Okay.
It's because of the way in which you make these things. But in terms of actually making these things in a reproducible way time and time again, what's the specific advantage?
For Langmuir-Blodgett?
Yeah,
but then you really control the thickness.
Yes.
Number of layers. For me, it was a nightmare to. I mean, there is depending on where you put this, like samples with in the oven, you will get different type of evaporation rate, and then you get different thicknesses, even if you start with the same condition.
One of the advantages of the laminar logic is that you can fix the number of layers.
And I guess it's quite uniform and so on the whole substrate.
Yeah, I mean, again, it takes a little bit of practice to do it, but it's also very, very slow. But saying that, I mean, a lot of your films actually consisted of what I would call quite thick layers. Yeah,
Yes.
so up to 70 plus layers.
Yes.
Now, how many layers do you need to get a photonic bandgap?
There is this article, I don't remember from whom, I'm very bad with remembering name, but they have designed these equations where from this, because you can solve, you don't have to apply this Weisner, you can solve the equation, the Maxwell equation, so they have started from there, and then they have introduced the geometry of, I don't know, I don't exactly know what they did, but they have a formula on their paper, and you can calculate for different materials for your colloidal what is the minimum, the critical number of layers that you need to get this photonic effect. And for polystyrene, I think it's 15 layers.
15.
Yes.
Yeah, I would have said 15. 12 to 15 in general. So, I mean, one of the things I think that in some ways your materials have suffered from, so there is an advantage I'll come on to, is that they are very thick. Yeah, and because they're very thick, they bring with them particular issues. So I don't think you needed to make them as thick to see the photonic band gap. But on the other hand, the way you were making them, it's actually very difficult not to.
Yes.
The advantage that you have is the robustness of the films. Because being thicker, they would stand up to handling a bit easier. Okay, let's move on and talk a little bit about photocatalysis. You showed us all a really nice slide which showed how the titanium dioxide operates. But the titanium dioxide is a photo and catalyst is the key word. Yeah, there it is. Okay. So after the reaction has taken place, what has happened to the titanium dioxide? If it's a true catalyst.
Well, normally it has recuperated an electron from reaction, so it should be neutral again. Okay.
Yeah, that's true. So it should essentially go back to where it started from. Yeah.
Yes.
So imagine now you've got your stearic acid, which is okay. There's a couple of carbons. 3. No, 2. And mostly the rest of it is just carbon and hydrogen. Yeah.
Yes.
And that stearic acid has now been totally mineralized through to carbon dioxide and water. So where does the oxygen come from?
Well, we have oxygen in the air, but there is 2 oxygen.
For the catalytic process itself.
Well, it can come either from water, so water have been already separated between oxygen and hydrogen, or I think it's
No, that's all right. That's okay.
So we can get this oxygen as well. But if you get an electron, for instance, you can get this highly reactive oxygen, so it will attach itself to.
And one of the things that you found was that you did find that it was difficult to correlate some of the photocatalytic results, particularly with the stearic acid. I think it was methylene blue. It was a little bit easier. There seemed to be some trends which you could observe, but the stearic acid in particular was a bit more difficult to understand.
Yes, I think it's because there were so many different factors that were not controlled. For instance, in the appendix of the thesis there is this the stability of the lamp, and you see that as the time goes on, so if I keep the lamp on for a long time, the power decreases a bit, so the power of the sample decreases. So this can influence, for instance, I have seen that for cores that are below 10 milliwatt, then I have I have an influence of the pore on the activity. And also, when with the sterilic acid, because I deposited with this spin coating, and normally I always try to use the same amount, but I mean it's still spin coating, so you don't control how much we get away from your, even if you keep the same setting all the time.
Yeah. No, I think, I think you picked up on this. I just, what I'm asking you to do is to tease out a very particular point that you make in the thesis, because I think it could help explain some of the, if you like, anomalies that you might have seen. So if you take your diagram here, you can see you've got oxygen and there's water involved, and you can get things like hot species radicals.
Yes.
You can even hydroxy radicals, you say here. You can even get, yeah, that's right. Okay, now imagine you cover that surface with a thick layer of organic goop.
Yes, then of course you can have a problem of oxygen accessing. But at the same time, I have seen this, there is this article from, I think, Mills and Mills Group, and they have, again, it's like a, I didn't verify this formula, but they have a formula where you can calculate what is the number of monolayer of sterilic acid that until which you don't have to worry about that it's the ideal working this pseudo rate pseudo first order, and then when you start to increase the number of layers above this limit, then you get this zero order. So when you change the regime. And normally, all of my samples are below this, so they're all in the same regime. Mm. But then, yeah, at the same time, it's like we wanted to have just one monolayer, and I think in some samples I might have one monolayer in some parts, and then maybe these I've explained why they were faster than maybe the one.
I think that's right. I think you make the point later in the thesis that the thinner films. What you think is a thinner film, or you calculate as a thinner film, actually does behave a little bit more consistently
yes.
than some of the thicker films. And I think it could just be down to the problem of replacing the oxygen, which has been reacted away in the catalytic process.
Yeah.
You know, if you do this experiment with TiO2 under nitrogen, for example, it stops very quickly because it just runs out of oxygen. You have to replace that oxygen from somewhere. In some of Andrew Mills's work, there's different kinds of samples, and you can get oxygen and water to diffuse through the film. But I suspect that your films might have been a bit thicker, at least some of them.
Yes. Yeah. So, I mean, it's actually something that is not easily controlled. I'm not so sure how it will be possible to.
Yeah. Okay.
How much you have in there.
Sure. Let's talk about fabrication methods. Obviously, this is something that you developed, and in particular, I was really fascinated by the iron milling stuff that you did. There's a lovely picture that you have in the thesis, which shows the result of what happens when you try and iron mill one of these samples.
Yeah, this one was an interesting one because I did the iron milling after removing the polystyrene.
Ah. Okay.
And so that's why it's this big.
That's a picture.
I think it's the next chapter.
Yeah, that's it. Is it 75? Or?
No, I think it's 75. Should be soon.
Yeah. There it is, that's right.
Yeah, so this one is the 500 nanometer diameter beads. And what I did is that I scratched, it was only one monolayer or two monolayer, the whole sample. And I scratched the side of the samples and I baked it because this was, I think, someone in the literature did that sort of work. Of course, the iron milling is a bit cleaner because then you are sure that you open all the structure. But I did have evaporated, at least in some places, the polystyrene. And then under iron milling, it has this very interesting effect. And I think it's because it's hollow. So then you only have this thin wall of alumina that is like a balloon. And then you bombard it and it just flowing. And I guess
I like that. I thought that's very interesting. And it just shows you what you can do. I mean, what was the thickness of the? Well, it's 2 layers, is it?
yeah, it's 2 monolayers, I think, on this one. But this one is only one. This image is only 1 monolayer. Yeah, I only have this one, but it's like this sample was like this 500 nanometer bit, and they were much easier to deposit than the 200 nanometer.
Okay. So the technique that you use to if you like, strengthen the structure before you remove the polystyrene is atomic layer deposition. Yeah?
Yeah, but basically.
Yeah. So I think you give a description of how atomic layer deposition works, and it kind of involves, so with your molecules, so for the alumina, it's trimethyl aluminium and water.
Yes.
And for the titania, it would be titanium tetrachloride.
Tetrachloride.
Yeah. Okay. So are there other precursors that you could have used for that process?
Yes, if I understood. No, but there is actually, I think titanium dioxide, a lot of people deposit it with plasma. So then you have, I think you start with titanium tetrachloride, but then you do this oxygen plasma in the chamber. So then you get this reaction the same way. Then for alumina, I guess it exists some other precursor, but I mean TMA is the one that is used everywhere.
yeah. People have started recently to use slightly different precursors that are less reactive.
Okay.
But usually because they're talking about a very high volume, large scale manufacturing process, and they don't want to worry too much about trimethyl aluminium. But why would you worry about trimethyl aluminium if you're using a lot of it? Did you do your safety evaluation on the precursors?
I guess it's not very good for the environment. But
it's not very good for the environment, no.
I guess it's kind of capture oxygen.
It certainly would.
Yes. So I guess it would not be nice to ingest it.
Yeah, best not to.
Want to breathe it.
Yeah, you wouldn't want to coat your lungs with aluminium oxide. This is true. Yeah, it's the compound is pyrophoric. Do you know what that means?
No, sorry.
It burns spontaneously in air.
Oh, okay.
So if you were to open the valve on the container, a little jet of flame would come out.
Okay.
As it burns. Yeah, so it's not very nice. The other one for titania, which is used a lot at the moment, is something called TD mat. You ever come across that?
I think so.
So this is. Do you have any idea what it's called?
No, I mostly search for my precursor.
I only say it so that I can sound clever. It's tetrakis dimethylamino titanium.
I would never have remembered even if I knew it.
Very good. Okay, now I think somewhere you've got sort of some schematics of how the ALD process works. And here I'm going to have to beat you up over a few things.
Sure, go ahead.
I'm sorry, it's just inevitable, yes. Okay, so essentially what you've got here is a reaction between surface hydroxyl groups. Yeah? Aluminium OH star, right? And that, sure enough, is exactly the mechanism that would be described in the literature. So there's nothing wrong with it. What do you think your surface looks like before you start to grow?
I think it's mostly.
What is it made of?
Well, TMA, I would say.
No, the actual surface before you even start to grow.
I guess oxygen.
Now, what are you actually growing on? Okay, so you've made your photonic crystal from polystyrene.
Yes,
polystyrene. Yeah, okay, so it's polystyrene.
Yes.
Okay.
I guess there is some. I mean, the thing is that we deposit at 70 degrees, so it's not high enough to evaporate water.
Yeah.
So I guess I have water to begin with.
Possibly, you might have. Yeah, you might have. It depends. Usually the ALD machines are flushed for quite a long time before you start.
But my sample will carry water.
So, do you think, for example, that the growth starts from the very first cycle?
No, for sure.
Good.
It's like the. I think for instance for titanium dioxide, I think it was actually a quite large number of cycles before I think I started to get a cycle like a real deposition, something like 50 cycles, something. But I think it's because my ILD setups were not optimum. Now I have realized that after. But when I was writing, actually, I found a thesis of someone depositing alumina on silica ovals, and his whole thesis was to design the best cycles, best temperature, best pressures, best waiting time, plus time, and so on, to deposit on this FCC. And then I realized that maybe in my I didn't want to waste too much material, but I think I should have increased my process time to have a better uniform deposition. Because since it's this closed path structure, I think you need a bit more maybe pressure to push the molecule inside the structure.
Yeah, I think I'm not really going to beat you up, but
just go ahead.
what the issue is that, and you very carefully recognised this in the thesis, that there was a considerable variation between the two machines that you used and the various conditions that you used.
Yes.
Okay. It's very possible to do the ALD experiment wrong. Okay, particularly if you have a very porous substrate, because ALD machines have been designed with the semiconductor industry in mind, where the substrates are invariably nice flat wafers. Okay. They're not designed for use with very porous structures at all. What you have to do is you have to really throttle back the pumping. And when you introduce the precursor, you've got to allow it time to get inside the structure. So this means that you slow the whole cycle down, okay? And you simply allow the gases to permeate throughout the whole structure. Now, modern machines are designed to do exactly the opposite. They coat flat surfaces, and then you've got to get the gas out of the chamber as quickly as possible, such that the cycle time is as quick as possible. Just by way of explanation, a typical cycle time in an ALD process can be anything from a few 100 milliseconds up to maybe 5 or 10 seconds. The problem that you have is that you only deposited, at best, 1/10 of 1 nanometer in that cycle. So if people come to us and they say, "Can you do aluminium oxide ALD?" We say yes. And they say, "Can you grow 5 microns of aluminium oxide for us?" We say no. Life is too short. We can't do this. We'd have the machines running for hours, days to do it. So I think some of your experiments were affected by the fact that the ALD machines are specifically designed not to coat textured samples. Mm-hmm. And you really have to modify the process to make sure that they do it properly.
Yes.
Yeah. You maybe have had to put in a few extra components, like a valve in the exhaust pipe, or a valve to the pump, so you can throttle it back. Yeah.
It's like the deposition time was quite long. Since most of the time this was between 6 and 8 hours. But it's still, I think, for instance, we can see here with the ALD on polystyrene, I think my pulse time was too short. So I had 4 pulses like in alternance, and with a purge time that was so.
Yeah, no, I think you're exactly right. What's the consequences of having a pulse time too short?
Well, I guess is that I think that that's why I have a difference in deposition between the sample, because then the gas have time to deposit and permeate the first sample closest to the input, and they don't reach. Not enough gases reach the end of the chamber or like permeate in the end samples.
Yeah, we sometimes call that underdosing. So you've introduced a pulse, and you kept the pulse as short as possible because there's no point in wasting your expensive precursor.
Yes.
But actually, for the particular substrate that you've got, where the
Actually,
surface area is huge, you haven't put enough.
Yeah.
So it's underdosing. I mean, you can use underdosing. It's a clever way of making half of a layer of one and then filling up the space with something else. So you can make mixed materials. But I think that some of the experiments suffer from underdosing.
Yes.
Yeah.
I agree.
Yeah. Okay, and you also talked, sorry, I'm jumping around a bit, I know here, but you talked about cracks as being significant in your samples. I think that might have been around page 94.
Yes, it's still somewhere.
Yeah.
Well, you can see 1.6.
Yeah, that's right, yeah. No, that's fine. So, I mean, you know, like most people who make photonic crystals, your samples have cracks. Okay, so it's not a criticism. Yeah, this is a fact of life that you get cracks.
Yeah, it's because
so what do you think is the fundamental reason for getting cracks in the sample?
it's when the water is retreating. So there is a function for it. Is it called function?
Yeah.
It has a name. There is this capillary forces. Yes. When the water is retreating from this, there is this. I mean, the beads are in the nanometer size, so then the holes between the beads are also nanometer size. So then when the water retreats, it creates a huge tension on the structure. And then you get these cracks. When the water evaporates, you get these cracks.
Do they matter?
Not really, but it depends if you want to really have this connected structure. So like I say at the beginning, when you have these holes that connect from the top to bottom, if you want to be able to connect from left to right, so for the whole centimeter range, then if you have the wall, I think you don't have these holes connecting because they are separated by hair. So when you deposit, you kind of block you make blocks of inverse opals, basically. So maybe if you want to use it for, let's say you want to make a flow of water passing through to clean it or filter it or whatever, it will be, you will need to increase the pressure, I guess, if you have these walls in between.
Yeah, I don't know about that. You might be right. I mean, sometimes you know, because if you come back to the main application area that you're looking at, which is sort of pollution and cleanup of pollution. You know, you've looked at stearic acid as a sort of a film that's been deliberately put on, and you've looked at methylene blue as an example of something that might be in water, for example, so an aqueous issue that has to be dealt with. And, you know, it's incredibly important because drinking dirty water is probably the largest cause of infection and death in the world today.
Yes, and
still,
the quality of water is everywhere.
Yeah, absolutely. Water quality is an incredible problem. Yet we have the technology which, you know, can deal with it easily enough. But the other thing I was going to say is that there's other kinds of pollution which a porous material with cracks in might be perfectly acceptable for cleanup.
Maybe oil spills or something like that? Oil spills?
Oil spills, possibly.
Because I have read some, I mean, Tiffany is very incredible. I read some articles from the 90s, and they were saying that you can actually break down some petrol, basic petrol molecules with titanium dioxide, and also like all type of bacteria and stuff. So maybe you could trap the oil or something in those cracks.
But also airborne pollution, for example, where you've got your pollutants in the gas phase.
Yes.
Yeah. So there's a lot of work currently underway looking at what are called NOx species, NOx, where X can vary, you know, from vehicle emissions and stuff. Titanium is being used extensively to try to see if it can reduce those. And there the problem is rather different because you've got things in the gas phase trying to permeate through things with holes in, by definition. And sometimes cracks could actually help. Where would the cracks not help from the point of view of what the aim of your work was? The overall aim. if you've got a material with loads and loads of cracks?
Well, it's,
What do you think it would do to the width of your stop band?
it will increase the lift, and it might decrease actually the photonic effect, depending on the range of, I mean, the period, on the scale of these cracks.
Yeah, yeah. I think that's true. Now, the issue of cracks is a tricky one. How might people try to prevent cracking?
There is a lot of funny study on this. Most of the time, it's and I find this idea quite good, is to try to deposit these colloidals on a more elastic surface. And I have actually tried. I haven't succeeded that much, but I have tried to deposit it on. I try actually to deposit it on a lot of different type of elastic substrate or like substrate that could be removed, for instance. It was not like super successful, but I read some article where people managed to deposit this.
Yeah. So you basically put an elastomer or something between the spheres to sort of hold them together and compensate for the drying stresses that are produced.
Yes,
yeah.
And there is also some people who made some deposition with more like a gel-like structure to maintain.
That's true. That's very good. Yeah. No, it's interesting. We come across opposition to our work sometimes, particularly from my institute, which is full of semiconductor device engineers. You show them a photonic crystal film, and they say, "Wow, look at the color. It's fabulous." And then you show them, you slip them an electron microscope picture, and they see a crack, and they go, "It's going to crack. It's going to crack. This won't." Yeah. So we say, look, it depends what you're using it for.
Yes.
Yeah,
I think silicon oxide-based colloidals are rather sturdy. I think it's in comparison to the polystyrene, where it's a bit more easy to like make powder out of them. So if I take my opal sample and I put my finger on it, I can just start to scratch them.
Yeah.
So the local structures stay quite well, I think. But
okay, listen, I'm going to jump around a bit. Let's talk about something which is a little bit inconclusive in the thesis, and that's what's special about 70 layers. Yeah?
I don't know.
So this is around page 133.
Yeah,
I think in that sort of section.
I don't know if it's an effect from because I have more
So
samples.
first we'll explain what the 70 layer effect is. 133 or in that region, I think, is where you start to talk about it. Yeah, I mean, okay. So this shows it. Yeah, you showed this in your talk. But just tell us what we're seeing again.
Well, this one I didn't show, but it's something similar. This one shows this diffuse. So when you measure the scattered light in the sample, in the spectrometer, sorry, and then I just divided by the total light, and so you see the proportion of diffuse light in the total light that make up the total light. And I don't know, maybe it's because I don't have enough samples, maybe in this range or something, but it really looks that after I start to have too much layers, then I start to increase. This means that the diffusion part in the total light increase a lot. So I have more scattering. And I think I see it again, for instance, here, where I try to do this absorbance thing. So when you remove the...
Well, 1 minus R is equal to P, so you do log of P.
Yeah.
Yeah.
And then it's like, it's the same. Yeah. This is a measure at 800 and nanometers, so where it's far away from the absorption of the UV of the polystyrene. And then I can separate really into two the like linear fit, if you want. And here it corresponds very well to what I have seen in literature of people having these measurements of alpha, this absorption coefficient. But then when I take separately this very thick sample, then I have like almost 100 times this alpha value.
Just remind me why you were looking at 800 nanometers.
Because I was far away from the photonic band gap and from the absorption edge of polystyrene, so I don't have to worry about effect of absorption, because if I have a thicker sample, then I absorb more.
Sure.
And then
well, saying that, I'm saying yes to absorption. Well, where's the absorption?
at 260. Let's see, I have some.
From the
Here,
polystyrene.
this is a polystyrene film.
From the polystyrene.
And you see that there is an absorbance on 262 nanometers. So then I wanted to be far away from here. And then usually when I have a polystyrene, I have a photonic band gap in this range.
Right. So
then I took 800. So then I just take the effect of thickness.
But 800 wasn't chosen for a very specific reason. It was just far away from where you expected the resonance to take place or the absorption.
So if you take here's the absorption coefficient. This is from two different literatures. It's a bit noisy, I don't know if you see anything. But this is in the UV, so you have this big absorption. Sure. And then in theory, in the visible, there is a bit of absorption like close by here, but then it should be relatively constant. So there should be no change normally.
Okay. And the other thing I was going to say is that the measurement of diffuse scattering in a relatively thick film is actually quite a difficult thing to do.
Yeah, I will guess that I have a lot of problem with that, I guess, because also if I have, with the design of the instrument that I use, if I have diffuse light that is too close to the edges, it shines directly into the detector. So then it's basically for what I've understood, what you measure as diffuse and what you measure as specular might not be strictly what you think.
That's right.
So there is some way of, I mean, there is a lot of like change that you can make, like parameters from you, that you can include in your equation to try to correct this effect. But I guess from what I understood with discussion with colleagues who work with optics, then what I could have tried is making some other type of measurements on this single beam sample, because then we have this integrating sphere, but we have only one opening, so then it's it's much less parameters to input in, and then you can compare both results and make corrections on your final spectrum.
So you did check there's no obvious correlation between thickness of the film at that point and the wavelength where the onset takes place. So you're looking at 800 nanometers. How thick is the film at that point?
Well,
how many layers was it then? So we're looking at 70. And these are 200 nanometers in diameter.
Yes, so it's from around 20 layers to a bit. I mean, after a while, I think a bit below 80, we are below the detection range of the instrument because there is nothing is too thick, so nothing passes through. So then we start to have this. I don't know if I can. We start to have this basically. The deep in the transmission reach zero for the photonic band gap, but that doesn't mean that we have like a perfect one. It just means that the transmission has dropped severely.
Okay. Yeah, no, I think that is a very interesting result. I also don't know why you see that. I'm a little bit worried that it could be an instrumental thing, as you mentioned. because of the design of the integrating sphere that you're using. It is notoriously difficult to get reliable measurements of diffuse scattering. But I think the answer, well, the experiment that needs to be done to solve that one is to use a different arrangement to see if you get the same effect with a different kind of sampling geometry. Yeah?
Yes.
For some reason I've highlighted page 142. Could you jump to 142? Just if my notes make any kind of sense.
No problem.
Okay. So, yeah.
This one now we are in the intermediate stage, so we have polystyrene and alumina, for instance, and they are still called opals.
Oh yeah, well, it's the structure. Why is it a really good idea to put an alumina layer underneath the titanium?
Do you want the clever scientific answer, or do you want the truth?
I want the clever. I want both actually.
I will start with the proof. The proof is that I did not get access to the ALD machine first in the clean room, so here in Oshun, because it was a new machine, so they took almost a year and a half to set it up. And then I had only access to the chemistry department ALD machine, and they didn't have titanium dioxide deposition. So we made a trial with alumina, and then my supervisor got the idea to still use them and make a double layers. And then we figured out that for my experiment in handling the materials, it look first of all, I think that the alumina was easier to deposit with ALD, so then we get much thicker films for less deposition time. And they might be quite sturdy as well. And then the second thing that I've noted is that it's easier to control where the photonic band gap will be from this multi-layer material. I think it might be that the titanium dioxide was easier deposited in this alumina structure because, first of all, they are both oxides, so it's quite different from polystyrene to oxide, and also the structure is more open. So I think the deposition, due to my mistake with the ALD, the deposition was easier on this multi-layer bonds.
Okay, so I think that most likely if you put the titanium down directly onto the polystyrene, okay, then because of the nature of the process, you might have introduced more disorder. You might have damaged the sample, and I think it would be almost inevitable that if there was any photoactivity, it would be dramatically decreased when you took away the polystyrene. Why would I think that?
What could be the difference with alumina?
So okay. In a way, it depends on how you did the experiment. If you put the alumina down first,
yes,
then the titania, then took away the spheres.
No, I didn't do it.
No, that's right.
Yeah,
Okay. Okay. So, but if you did do that, okay, that would still be okay up to a point, except that, as you say, it's more difficult growing the second layer because you reduced the pore size.
Yes.
Okay. So what you did was you put the spheres down, then you did the alumina,
Yes.
then you took away the spheres and put the titania down on top. Okay. Yeah.
Yes.
So the beauty of that is that you've got the titania both sides of the alumina. Nice. Yeah.
Yes.
But the other thing is that if you didn't have the alumina layer down, how do you then take away the spheres?
Well, it's the same idea. I do ion milling. I mean, I did.
No, to get an inverted structure. So let me. I asked the question about it. If you just made a polystyrene opal,
yes,
and did titania ALD,
yes,
how would you get the inverted structure?
Well, I actually did it. So I did exactly the same. I mean, I went to the ion milling machine. I removed maybe the first 2 layers of beads, and then I just bake them.
Yeah. What do you think happens to the carbon?
You think it's yeah, but I might have polluted.
Contaminate or whatever. Yes.
Yeah, but yeah, I guess I got some carbon. Actually, it happened that I made, for instance, I didn't make enough ion beading, and or I set up the oven too fast, because I think the oven cycle is very important also to be sure that you don't burn the polystyrene, because it has actually happened. So I have some samples where they are still photocatalytic, but I think it's like half carbon, half titanium. And I am not used.
Yeah, no, I think that's a very good point. And if we jump right the way back to the window glass that we talked about right at the beginning, if you put titanium down directly onto ordinary soda lime glass, it's not photoactive because there's too much contamination from the glass. So when the glass makers make the self-cleaning windows, they first put a layer of, not alumina in this case, they put a layer of silicon dioxide grown from silane directly onto the glass surface that acts as a barrier layer that prevents stuff diffusing into the titanium layer that goes next. I think that some of your samples probably had carbon contamination.
I guess so.
And I think having the alumina there would have helped prevent it.
Yes, so I guess that's also why it's much easier to get this, because I have several samples where I don't have. I had a photonic bandgap that was conserved after the deposition, but after the emulsion it disappeared. So I guess it's something maybe like that. I don't know.
So another really interesting thing that I think we found is to do with the shrinkage of the layers. I've not seen the shrinkage of these layers in inverted structures like this studied in such depth before. So I quite like that. But just talk us through your argument about how the shrinkage varies with the thickness of the film.
To be honest, I was surprised. I was expecting the contrary, so that when you have less thickness, you will have more shrinkage. But then I was thinking that we are talking about a very close packed structure, and that when you do this inversion, you burn away the polystyrene, so you have a lot of like pressure, I guess, of this gasification from the polystyrene, and maybe when you have these thick walls, it's kind of impedant to the evacuation of the degraded polystyrene, and then I guess there is also less place for because you have these holes. I'm not explaining very well. Sorry. I don't know if you can see anything from here. You know that when you deposit in the polystyrene, you have 2 different types of volumes in between, and there is one volume that is smaller. So when this one is filled, then you cannot add more. All the bigger volumes are still open, but you cannot add more in it. And I think that when you have a lot of this, so you have like a thinner sample, then it's possible to expand in this direction. So it doesn't need, when you have a lot of thickness, you cannot expand here. So I guess it's kind of like shrink. So you have to move in some way. I don't know.
I don't think that's wrong at all. I think it's very, very difficult to gauge something like that. But what I do think you've found is something that's very interesting. And in some ways it correlates with just ordinary studies of layer growth, even on flat surfaces. But the interesting angle there is to do with the morphology changing as the layer gets thicker. So when you imagine, particularly by ALD, you imagine layer by layer, following the contours of the substrate and all the rest of it. So automatically in your mind's eye, you think of lovely flat layers, but they're anything but. And particularly with titanium, you get very, very rough surfaces produced. And the roughness varies with the thickness. So I think that there is varying degrees of densification that becomes possible, particularly after I don't think it's necessarily the gasification of the polystyrene. It's essentially an anneal, what you've done. You've annealed the material by putting it in the oven and burning out the polystyrene. I think as far as the material is concerned, that's just an anneal. And I think at that point, depending on how thick it is, depending on how rough it is, the variation will change. And that is entirely consistent with other forms of thin film growth. So I think it's very interesting that you pointed that out.
Yeah, I had a lot of difficulties actually to find articles. Well, maybe I didn't put the right words, but I had difficulties finding articles on mostly on repeated heating. So there is a lot of articles on where you heat a material at different temperatures and see this densification. But it was very hard to find something about the time of when you heat. I think I found only one article where they had varied the time. So they keep the same temperature, but they varied the time like 10, 20, 30 hours. And observe this densification. So I guess it does make sense that if you just heat it up for 30 minutes or for 30 hours, it will make a difference, I guess. So maybe there is also this that's taken into account in comparison to others.
I think it's one of the most important things I think in the thesis, because it kind of demonstrates how you would go about making a self-supporting yet highly porous structure. Now, you've tried to use this for cleanup of pollutants with, if you like, variable degree of success there. But there are all kinds of other applications as well. Effectively, what you've made is a structure which has got a unique refractive index, okay? Something that will be almost impossible to simulate with another material, yet it's rigid and robust enough to be self-supporting under the right conditions. So, you start to think about things like waveguides and how you might use the material for that sort of application. And for that, you really need to know about the dimensions very precisely. And you need to know how much material is in there, because refractive index is key to those things. Yeah. Okay, well, let's press on, because I'm conscious of the time and how long you've now been talking.
Oh, I don't mind.
Okay, so that was really an interesting study, which we can call EB, effective baking.
This one is super weird. I'm not totally sure. I actually had debated with my supervisor to put it there or not, because I guess it was not entirely understood and not entirely clear that there were an effect. Yeah.
So no clear conclusions is what I wrote. Yeah.
Yes, exactly. Because
so is it densification or not? What's going on?
It's contradictory, because the thing is that if you have densification, then you should have it here. So basically, we are talking now. It's the same sample, but since when I do photocatalytic measurements, I put things on it, and if I want to use it again the next day, I need to clean it for sure. And I will not just let it in the UV and wait to be 100% sure that it's clean. So I just put it in the oven again. And I have noticed that some of the samples I have made, some of them I have used them a lot. So I have made 15 baking and something like that. And then when I made, I don't know why I got the idea to measure again the optical property. But I guess I started to get curious to see if I have a degradation of my sample. With different baking, and I saw that I have different, I have a reduced absorbance, but in the UV, but then I have an increase in the visible. And normally, I think from what I've seen from literature, when you have a densification, then normally it should be more, it should be more transparent, or is it?
It depends.
But I try to check for.
So, you can think of it as before densification, you've got your air pockets. which is what you talk about. Yeah.
Hmm.
Okay, so that what they're going to do is they're going to reduce the refractive index. Okay, how that then affects the reflectivity or the transmission depends on the wavelength.
Yes.
It's not immediately obvious. I mean, what I was going to say to you was that I can see why this got to you. But what you have to be absolutely sure of is that you're comparing like with like. Yeah.
Yeah.
So what would happen, for example, if one of these, if you had more water inside or attached to the structure?
Let's see. Well, more water. Well, I guess the transmission.
Well, I mean, in a certain region, you wouldn't really expect much to happen, but you're talking about subtle effects. You know, if you're looking in the visible there,
Yeah.
say 500 to 700, it's not a huge difference.
No, it's not a huge difference.
No. And I think you'd actually need some quite complicated modelling program to see what the addition of some material with a refractive index of say 1.3 might do to it. So, yeah, what I would say to you about this is, although it's inconclusive, you could probably get the answer with a few more sort of cleverly contrived experiments. But I wouldn't beat yourself up over it. I don't think it's that important.
No, but I made these experiments to really check if I still have a photonic bond gap.
Sure.
And then I was curious as why there a difference like that.
Yeah, but you know yourself. I mean, if you take a photonic crystal and you dip it in water, its properties change.
Yes.
I mean, people have detected. People have shown that if you take an organic liquid with a higher refractive index, you just dip your photonic crystal into it, the color changes completely.
Yeah.
And they say, look, it's a sensor. Well, you've got a bottle of the stuff, so you don't really need to detect it, do you? But you see what I mean?
Yes.
It's a rather crude sensor, I think. Yeah. Okay, just a couple of questions then on the photocatalysis measurements. You showed in your presentation the infrared peaks of the stearic acid. What do they correspond to?
Well, it's a vibrational bond.
They are. What one?
It's a double bond here. It's the carbon and oxygen bond. So you have a double bond and you have a single bond, and I think it's one that you get.
The carbon oxygen double bond is going to be much lower than that. Yeah? The oxygen hydrogen bond will be
They will be
higher
lost.
than that.
They will be lost with the water signal.
If you take a look at your stearic acid,
Yeah.
What's the most common species that you've got in the structure?
Hydrogen.
Yep, carbon, hydrogen. So if you go to your spectra, that's carbon hydrogen stretching, symmetric and asymmetric stretches. That's why it works so well. It really is focusing directly on the backbone of the molecule. You could try to look at the carbon-oxygen double bond. The trouble is that would be much lower down in wave number terms.
Oh, okay.
And when people originally did these experiments, they took a glass slide with a layer of titanium dioxide on it, and then put the stearic acid on it. And they did a transmission infrared experiment right the way through the slide. And because of where glass absorbs, you can't see anywhere below 2000 wave numbers. So that's why they looked at the CH stretching. So, I mean, you might want to just, for the sake of completeness, just label one of these figures CH stretches or something like that. Because that's what they are. Yeah, the carbon hydrogen stretch. Right. I did get confused with some of the symbols, but that's just me. You clarified it during your presentation, I think. So, listen, I'm going to wrap up now with my questions, but I'm not going to let you get away just yet. So, I think we've covered most of the important things that I wanted to raise. right at the end, I felt that you were a little unfair on yourself.
But really, if you would have, the thing is that I managed to do this inverse opal, and like after 2 years and a half. It took a long time to get enough samples to get started, and I was still doing experiments while I was writing, which is never a good idea. But at the end, I was very tired of getting this scattered data that I tried to understand why I got this one here and this one there, and it's the exact same condition, it's the same sample, and then I got, here is a good example. I mean, this is the 2 dots, here 2 dots, 2 dots, 2 dots. This is measurements I made in the same condition, in the same sample, and then yet we get this quantum here is completely different from one another. And I just got a bit pissed off at photocatalysis in general.
Well, I mean, you know, you mentioned in your talk about the need for standardization. Okay, if Andrew Mills was here, he would have jumped up and run to the front and slapped you because he's done quite a lot of work on trying to get standards. But you know, it's an incredibly hard thing to do.
Yes.
I mean, let me just give you a for instance, right? For some of your photocatalysis measurements, you used xenon arc lamps.
Yes.
What other radiation does a xenon arc lamp produce? So you've got your UV, yeah, that comes out of it. What else? Can you see it?
Yeah.
Yeah. Okay. So visible.
Visible.
Does it stop at the visible?
Does
it get warm?
It does infrared as well.
It does infrared as well. So
yeah.
The mere fact that you switch on the lamp means you will heat up the sample if you're not careful.
Yes. Well, my sample was quite far away from the lamp, so and I mean the thing also with the steric acid measurement is that I used this gold mirror, and it was not ideal. This was just because we had it and we had not time to order anything else. And you can see in the appendix, I think, it's page, where is the page? Page 259. You see the reflectance of the gold mirror. It's very low. So I think the temperature on the surface of my sample was not so high. I mean, the temperature outside, the lamp has a cooling system.
Sure.
Because it does heat us a lot.
It does. I mean, when people originally started to do these measurements to try and standardize the process, sometimes they went to enormous lengths to try to stop the infrared from reaching the sample, simply because maybe their lamp was closer to the sample than yours was. And so they would just get thermal degradation of the material, or if they were looking at photocatalytic destruction of bacteria, maybe the heat just killed the bacteria. So they would put a water filter in the way, and the water filter would absorb all the infrared. So it's very, very complicated. It's very complicated indeed. And you know, I'm not surprised that you do see the variation. And you know, I think you've identified the cause of it. You know, you had the lamp fluctuations that you measured on a kind of a daily basis. The power output that fluctuates. So I think you correctly identified the reason for some of the, if you like, variability in the results.
Yeah, but the thing is that I calculated the quantum yield. So then normally I should take the quantum yield take into consideration how much power I.
Of course, I know it affects the result. This is it. But you know, I think nonetheless, you've still demonstrated that it's possible to have photocatalytic photonic crystals.
Yes.
The jury is still out as to whether there is an effect or not. I don't think you could say that you haven't seen something. I think it's just the way in which.
My conclusion is really that there is an effect, but you cannot detect it if there is an added effect from power and some.
Okay, so this is just me, right? This is just me. This is just the way that I would tell my own students. There's no such thing as a good result. There's no such thing as a bad result. It's just a result. And how you interpret that result is what matters. Okay. I don't think you've been guilty of over-interpretation because you've pointed out at each time when you've found variability, I think you've pointed out that variability and you've tried to explain why. Now, okay, you're not going to save the planet with these materials, unfortunately, but you shouldn't be sad about it, okay? Not in a scientific thesis. Sadness is not appropriate, okay? In a scientific thesis, you should be very happy with the fact that you've looked at this problem, which is, you know, a very, very difficult problem to look at, and you've made some considerable progress. I always say sometimes it's the experiments that didn't work that actually tell you more about a system than the ones that do.
Yeah,
So,
but I still feel frustrated because, I mean,
we can be frustrated, but not sad.
yeah, but I have been educated as a physicist, and as a physicist, it's like I cannot make any conclusion if I don't have at least 100 experiments for each sample. And of course.
Okay, so the correct conclusion to reach is that you can't draw a conclusion.
Yes, but it's frustrating because I wish I had the time to make more measurements, because then if you have a statistics. If you have the statistic distribution, it's much easier to draw a conclusion.
Okay.
Or at least to be sure about you.
Yeah. No, I just thought I would end with that comment, and that's a personal comment. It's my own personal viewpoint. It's not meant to be a criticism.
No. I know, but then I can say criticism. I don't think this is what I mean, is that I think that there is circumstances that make it that I have not enough time to make as much statistics as I would have wished. So this is what transpires from this last chapter, this photocatalysis chapter, is that I feel very frustrated because I feel that I could have gotten maybe an answer if I had more experiments, so more repeated experiments.
Okay. Thank you, Mr. Chairman.
So, thank you very much for a very thorough examination. Now I will turn to the committee and ask if you have more questions. Start from this side with Professor Kessler.
Yes, so first and foremost, it's huge and very entertaining writing you made, and a lot of work. It was very interesting to read. Because I'm coming from very different domain in molecular chemistry and crystallographer, so in some points I felt we were in practice speaking different languages. So I want to ask some maybe questions concerning this. And then there are some points we probably have different points of view on. So to start with, on page 13, I think it is just speaking different languages. You write, for instance, titanium dioxide, TiO2, possesses a metal atom titanium and has 2 oxygen atoms attached to it.
Yeah, well.
How many are oxygen atoms each titanium atom is
No,
attached to?
it's more than that. But it's, let's see, isn't it octahedral? So it's like
Yes,
8
absolutely.
or something like this.
No,
Octa, no, 12. No, wait.
What does this word say? Octahedral.
Yeah.
It's 8 of what?
Of 8 is.
It's easier for us in Swedish because we have the same root.
Well, in French as well, I guess. But I can't remember right now.
It's 8 faces, but how many corners are in an octahedron? 6.
6.
Yes.
Yeah.
So it's 6 oxygen atoms around each atom.
Okay.
Well, on page 18, you have a very interesting explanation of color in simple absorption. You wrote, as the light travels in air and encounters an obstacle, say a red object, thus all colors with higher energy, all with shorter wavelength than red, have passed through a have been adsorbed by the red object. The red light is therefore the only color reflected, so the object appears red.
I guess I was thinking on the visible more than anything else.
I would say I would not completely agree on this idea.
Okay.
Because the experiment I give to my students, it is to explain to them the spectrophotometry. I give them a solution of a copper complex, which is deep blue in color. And when they record the absorption spectrum, they see there is quite a sharp single line of absorption because there is only one energy transition there, which is at 620 nanometers, which is orange. So how does the apprehension of color work in living beings? What we see is red or blue. Why is it red or blue? Is it only blue color that comes to us? The only part missing is around 620. It's orange. Orange is missing, we see blue.
Yeah, but this is like the dominant color as well. I mean, the blue is stronger than red.
Do you remember the color circle?
Yes.
Yes, because certainly we have gone through this. Our eyes, they're working on compensation principle. They work in anti-colors. So it's orange disappearing in the complete apprehension which we have for visible light because we don't see any other.
Mm-hmm.
We pick, or the biochemical mechanisms pick the color which is opposite in the circle. So red means the green is missing, generally. All the others may be present.
Okay.
Okay. Then some more questions. On page 27, just to test your description in crystallography, these indices, H, K, and L, what do they stay for?
Well, this is how you define
Exactly.
this is a definition.
So what is the definition?
Well, you have this. Well, you can see here that you have this axis like a Cartesian axis x, y, and z, and then you have this. You make a cube, and the highest is 1, 1, and 1. So you make a cube of 1, 1, 1.
Yes.
So then you define this like it's shown here. If you have this Miller indices, this HKL correspond to the X, Y, and Z, and then you have like here it's 1, you have 1 X,
Exactly.
and then you have 0.
So the 200, what is it staying for?
Well, but then you have like the point, and then you have the plane.
Yes. So you have absolutely correctly indicated the plane 200. Why does it have indices 200? What is 2? Yes, you have numbers.
Yes, but
H is 2. Why is it 2 for this plane?
It's let's see.
Because it's cutting the
It's
paper
cutting
meter with.
at the middle of
Yes, at the half.
the axis.
Yes,
Yes.
so it cuts by 2, therefore the index is 2.
And
Yes.
then it's
Exactly.
parallel to the other.
Yes, because all others are 0. You have an interesting figure on page 13.
Oh yeah. Yeah.
Do you understand what I want to ask you about?
I think, and I'm not so sure we'll be able to answer you, but go ahead.
Yes, you have circles.
Yes.
And you have empty circles and you have filled circles.
Yes.
And you wrote that empty stay for holes and filled stay for electrons.
Yes.
And I would not agree with you.
Okay.
So what do they stand for? T to G, E, G.
No, this is
3 and 2.
Isn't it well what we call in French case where you can put two electrons, one spin up, one spin down.
Yes, orbitals.
Orbitals.
These are orbitals. These are filled and empty orbitals. Yes, exactly. Okay. On page 41, you are discussing catalysis. You have an interesting graph. Again, as a chemist, I would disagree with you on this graph. Because one, the upper curve is showing the energy diagram without a catalyst.
Yes.
And the lower should be showing the energy diagram with interaction with the catalyst.
That's what I need.
Yes? Is it true that with catalyst you will have only one intermediate state?
No, I mean, no, because obviously you need to have the electrons on the holes.
Well, on interaction with catalyst, you will have a step where you have a complex with catalyst. So necessarily you will need two steps. You will need two activation energies. So there will be 2 pounds, not one.
I just wanted to have like a showing the idea, the concept.
Yes,
I don't know.
yes, I realize
I think
this,
my
absolutely.
supervisor had about a hungry. To be honest, I was a bit tired of like redoing.
Okay.
What are you my fault this one?
On page 49, you have also very interesting image. And as chemist, I absolutely need to ask you a question because you have identification of atoms.
Yes.
And the black ones are carbons, and the gray ones are hydrogens.
Yes.
Yes. And in the first line of the text, you have the formula for this. Actually, it's cation. Yes. So in this formula, you have C16 and H18. Yes. Some of what?
I don't remember.
Yes, and where they should come the extra ones.
But I think it's because we don't see them. They are in 3 dimensions. So there is some missing over there.
Yes, on methyls.
Yes.
Exactly.
But it's because they are.
Okay. Okay, I agree. Crystallography, I can say yes sometimes. Yes. Okay, very good. So last question, a more philosophical but also important. You have used ALD for creating your photonic crystals. And then you have referred to 2 other techniques, to sol gel and to just baking of nanoparticles.
Yes.
Why have you chosen ALD and what are, in your opinion, advantages and disadvantages of all 3?
So we actually wanted to start with sol gels because it's wet chemistry, so you can do it on the table. So you don't have it's faster. You can just let it happen, the reaction. So it has a lot of advantages. And I think the only thing is that you cannot control how much you put because you feel everything. But for some reason, we didn't manage to have the sol gel was just washing away the polystyrene. And when I was baking the structure, I only got a very small amount of photonic crystal, like very ridiculous amount in comparison. And then I tried also with the nanoparticles. So like it was people are called co-deposition. So you introduce these nanoparticles of titanium in your colloids, and then you deposit them at the same time. But the thing is that we had a problem with, I think, pH of the solution, so that somehow there were no mixing between the two. I didn't manage. So maybe it's because my polystyrene were commercial, and even though they say there is no surfactant, maybe they added some surfactant or like a small amount or something. And I never managed to make any mix of the two properly. I try to redo some. There is some people who have done it, and so I try to redo the experiment. But I think they don't really tell you exactly the recipe, so that you have to figure out for yourself like the correct way to prepare your solution to be able to mix them together. So I would think. I mean, the IAD is very nice because it's a physical process. I'm more of a physicist, so it was easier for me to go towards it. But it's costly and it takes time. I think wet chemistry is mostly if you go to the point of view of industry or like industrial amount of things, wet chemistry is much better.
Yes, as wet chemist, I of course agree with you. And I can also tell you that commercial titanium particles, they contain a lot of sulfate.
Yeah, so I would have guessed because actually we wanted to try the longer blotted method because it's you control more of the thickness deposition, the particle. Just it was impossible to make them float. We tried different. I tried actually for 5 months or something, like trying different, introducing some ethanol or whatever. But it never worked. So then I just give up and just check what people did, and then I just did my little cooking. That's what. Okay.
Merci beaucoup. I'm fully satisfied with the answers.
Thank you. Now we go on to Professor Galli.
Thank you very much for the presentation and the thesis, which is very rich. I will try and some questions I'm more curious about on the photonic side, because I belong to the category that Professor Van mentioned, the ones who fabricate from top down. So it's really interesting to compare. One first question I was thinking of, it came through in the discussion already, about the ALD deposition. In a thick layer, do you expect it to happen with the same conformal coating and uniformity through the thickness of the layers?
I would say yes. I would expect that in the vertical that it will be more conformal than in the horizontal actually, because there is this like they don't call them needle, but I call them needles. The little tube that introduced the gases. I think since I was in this regime of like underdosing, then that means that I think I had like a gas of precursor in close to the input, and the farther away I go from it in horizontal, the less I have of it. So I think in some of the samples I actually saw with the SEM images that I have somewhere, I have few depositions in the same sample, and then when I go maybe I don't know, like a centimeter away, I have like a thicker deposition. So, but I think from the bottom, I have actually scrapped some samples to observe them, and they were deposition on the bottom as well.
That's what I wanted indeed to ask. If it is structural characterizations, do you have an estimate of how much that variation might be across the area you are measuring with your lead, in the sense that you are something of quite large area, if you have millimeters. So what would you expect to happen to your band gap?
I guess it will widen because then I change the filling factor, so I change slightly the photonic band gap position. So my view on the sample, since I measure over a millimeter square area, I think I have a superposition of the photonic band gaps.
And that makes it very tricky to track because you're getting the full response. So that's about the standardization. I will now talk about the optical part. Standardization, can you think? You mentioned talking to your optics colleague and do some measurements which maybe sample smaller areas and where you maybe can do some angular and
yes,
frequency selective excitation and mapping instead of, because tricky. I mean, it's
yes.
a huge problem to work out from the integrated sphere output. What is happening in such a structure which might have non-uniformity inside?
Well, actually, the thing is that, for instance, so let's see. The first thing is that you need to have a lamp that's emitting the UV, or at least for the photonic crystal I'm in, for the inverse of that. There is a setup in the physics department where my third supervisor is working, and they have designed an equipment where they can change both angles. So they can change the angle this way and they can change the angle this way. So we made several measurements, but on the opal samples. But then the opal samples are much less interesting because it's not a complete band gap. So usually what you see is that if you are in the normal incidence and then you start to shift to measure, you lose the photonic band gap. So then there is nothing else to measure. It would have been interesting for me, of course, to measure the inverse of Hall, metal oxide inverse of Hall, with this angle measurement to see if I keep this. But I have a complete band gap. But the thing is that they didn't have the UV lamp. And then in all laboratory, we have some lamp, but it's the same as we use them for, we want to use them for the windows, the smart windows. So then it's the same, it's solar. It is kind of like solar illumination. So they were talking about bringing it on, but then I started to write my thesis, so it was already too late. But I really wanted to do this, to have this, because then they could really change the angle, and then they could make some filters to change the wavelengths as well. So it would have been very interesting.
And you could maybe attach a figure of merit to your samples that then allows you to track the performance. So that's again to link to Professor Campbell's comments about the approach and being frustrated. I think there is a massive amount of things that you learned from that can be useful to. So that's the classical question. But if you were to do now with that knowledge again, to plan the sequence of fabrication, characterization, optical and photocatalytic experiments, how would you go about it? What would be the guidelines or the choices that you would make to?
But I think I will keep my. First of all, I will ask for an environmental chamber where I can control the temperature and humidity, because there is a lot of people who have made measurements on the effect of humidity and temperature on these colloidals. And usually you have a window of temperature and a window of humidity where you get this less defect and more perfect structure. And I think for a lot of my deposition, since I'm in this ventilated oven, I have a very low humidity. And then I might have been in close to the border of this edge where it starts to be a bit bordered. So I think I will go first with changing my deposition chamber, so I could have better control on humidity. Then I think I will stitch to ILD because it works, but then I will obviously change my length and my pulses to introduce the chemicals. Then let's see. I think the fabrication will remain relatively the same. Then for the optic, I think I will beg the physics department to get this UV lamp so I could make this angle measurements. That's a definitive. And then for the photocatalytic part, I mean the setup. I think the setup are very similar to other people's setup, so I could still continue to use them. But like I say, then I would really want to have more measurements per sample, or maybe select 30 samples instead of, because now I had close to 70 samples. So select maybe 30 samples and then measure only this, but maybe at least 10 times or something, to have more statistics and maybe more reliable thing. But then. If I would have like unlimited budget, maybe I would say order some new machine where I can control everything. I introduce certain humidity, or actually there is a colleague who did. He made he sputtered titanium dioxide. And he has designed a window where he can introduce the chemical he wants to degrade, but then he could control the humidity and temperature inside this small chamber. So then he had made a systematic measure of the activity of the film depending on this humidity and temperature. So maybe something like that with the photonic result would be also interesting.
And between the two reactions that you are dealing with, would you prefer one or which any example?
Well, it depends because I mean the methylene blue is very controversial in the field because it can degrade. You can lose the color not through degradation but through reduction. So then instead of oxidation you get reduction and you still lose the color. But then there is this. We solve the problem with this magnetic stirrer. So hopefully we have introduced enough oxygen. But then the stearic acid, it was also the thing. I don't like the atoms because they are stable, but they produce a lot of heat, and they also degrade. For instance, my last experiments, the lamp actually died. So I'm not entirely sure if my last maybe 2 or 3 days experiments made with this dying lamp were the same as 2 weeks ago. So I think I would have tried also with maybe with some specifically designed LED lamp, for instance. Sure.
One is, well, you mentioned this one, the disorder, and I was thinking maybe roughness of the structure and stuttering. And the fact, I don't know how your process, if I understand correctly, would not be applicable to thinner layers, or do you think that if you grow thicker, you might even start having more roughness and non-uniformity, which degrades performance?
Well, it depends on which step of the fabrication I think you think of, because because I think for the ILD, if you have the correct cycle for ILD, so the right time length of pulses, I think the thinner sample will be actually better. They will be more uniform. And actually, I'm a bit annoyed with the ILD machine actually because I don't understand why they don't have a rotary stage for the sample. I have asked several people working in ILD and they were like, they don't know.
This is the thing, something. If you're doing the ALD correctly, you don't need it.
Maybe, but it will still improve quite a lot. So
It
uniformity.
wouldn't make a difference. If you're doing it right, it will work. If you do it wrong, it won't work.
Anyway, so it's like so then yes, if for the ALD process, I think if you had thinner sample, it will work better. But it's like when I try to reduce the concentration of the colloids, so when I made the first deposition, usually it was not uniformly deposited. I think there were not enough polystyrene. So then I kept to like a relatively high concentration, but it's quite common in the literature with 0.2 W weight percent. So I don't know. I mean, you need a minimum of 15 layers for the opal, but I guess my sample, some of them are too thick, for sure.
And when you do the optical measurements, are your samples like suspended structures, or do you do them on a substrate?
They are on quartz substrate. I actually try to deposit the colloids on photoresist, for instance, to be able to remove the sample, but it didn't work on photoresist, on at least the one I had bought, and I tried to deposit it on melted polystyrene film, and it didn't work as well. I think I tried this. How is it called, this resist? But then it didn't really work. The inversion.
Do you think that can affect your optical measurement? And maybe even your 70-layer effect if you have.
What do you mean if I change the substrate?
Yeah.
Yes, well,
Is it correct for that?
I'm not entirely sure because it's, I mean, it's always just a thin layers. I mean, I made measurements. For instance, I tried to make deposition. This is just some quartz, and then I tried to make deposition with this photoresist that was spin coated, and PMMA, which was also spin coated, I think. And well, you can see that the deposition, the yellow part is with photonic crystal, and you can see that the deposition is not very successful here, and here the surface is quite rough, but where it's flat, it has been working. And I think the optical data was not extremely changed by this thin film of like photoresist or PMMA.
And the quartz absorption and property. What I'm thinking of is that the effect that you see the change with the 70 layers, if you take your picture with the effective index of the porous structure, then you're drawing a thin film which has an effective index, and at some point, maybe you're familiar with a anti-reflective coating, you can have an effect of interference between.
Yes,
And that might occur at specific thicknesses in relationship to the wavelength that's your vision. So that's connected in a way to.
yes, we were actually wondering about that, but I never got
Or do you think of any experiment which would allow you to work with that? Okay. Optical.
let's see. Maybe, well, I don't know because it's, I mean, it has to be an optical measurement, and I cannot see of anything else. But then, which optical measurements? I don't know if I know enough about how to design one. Actually, I was very frustrated because I saw that I could not do ellipsometry on the inverse valve, but apparently I read an article where, well, the thesis actually of the person I was saying that deposited, I mean, on silica, FCC, he had actually made ellipsometry to measure the thickness of the deposition, and I don't know if something like that could be used on the opal. Maybe because on my license plate I have some of the.
I think essentially is if you consider constant thickness, then it can help if it's an interference effect. For example, in wavelength, we see if interference is occurring.
As you can see in this one, it's the optical measurements of this, like this sample with photoresist and so on, and it's like I don't have anything. This is just a photoresist, for instance, or the PMMA, I don't remember. So there is no interference with the photo. That was just okay.
Okay, and Dr. Barlow.
I also agree that a lot of work has been done, and it's quite interesting work, and I guess it's only natural that some question arise. And first, my question regarding color. In the beginning of the page, well, you wrote, for each color we can calculate a specific energy and a specific wavelength. Is it really true?
Well, I saw it's how you define the color.
Well, it's a question for you, how you define the color. It's a color defined, well, it's exists, for instance, color coordinates to measure color. And it means that if I understood you, if I will give to you color coordinates of, for example, for this butterfly, there are several coordinate systems. It can be RGB or X, Y, Z. This means that you can give me answer regarding energy of light or
Oh,
wavelengths?
the tricky question. Actually, I don't know. As a physicist, I see light as a wavelength or energy. I guess I never really wonder about if I could define the printer colors in terms of energy. Well, but I mean the colors. I mean you have the base. You could still. Well, I see what you mean because now this color for the butterfly is not just blue. There is some like green and so on. So
But that is also color. It's
Yeah,
in a
that's
color diagram you can find a specific this color and find coordinates of this color. A question is can you according to this color
No,
for
I
instance find the spectrum of light that correspond to this color.
well the spectrum.
Well, if
But a specific energy range. No,
energy or wavelengths or it
no,
doesn't matter.
not a specific. Okay, I see. Not a specific wavelength because the specific wavelengths correspond to only one color. I mean, like one of the primary color.
Yeah, but the color is a more.
But this one is a combination of several energies.
Well, and that's why I'm asking you that it's a color. Color is measured in well, in a
Okay,
color,
so maybe
but
the choice color is not right, but
I also think that it's not the best solution to operate in color because after that also I found several sentences where you operate in terms of colors. If you have, for example, spectrum of light, it's no problem to determine color, but not inverse operation. At least in a general case. If you know that you have a monochromatic light and you know color, in this case it's no problem, but if it's not monochromatic light, it will be a problem. And the next question on the page 21, you mentioned that photonic crystal consists of two dialectics arranged with periodicity.
Mhm.
And I'm wondering, is it always only two dialectics? Or
well,
can it be 3, 4, or 1 dialectic?
one district don't think it's possible because I mean you need a contrast. You just don't need just a periodicity. You need a contrast between two different mediums of light circulating, and then I think one of my supervisors, sorry I don't remember, mentioned that there is some people that make calculation and were saying that if you have more than two materials, you cannot really have a photonic crystal. But I mean, obviously, I got some. Maybe I don't get a complete photonic band gap, but when I have this multi-layer alumina titania inverse, I do get a shift between the alumina titania. So I do have an effect on the photonic crystal. I do have a photonic crystal effect, but I don't know if when you have a double layer, if you have this complete band gap on the whole direction of the gradient. But I don't think if you have just one medium, you can have a photonic band gap.
And as for 3, 4?
Like I say, it depends which type of photonic band gap you want to obtain.
Yeah, but if we are talking about, well, in a general, photonic crystal can be photonic crystal made from 3 or 4 different dialectics.
Well, from my experiment, I would say yes.
Okay, but you think that it's not possible from one dialectic?
Well, I don't see how you can create periodicity if you only have one.
Okay, and you demonstrated in your thesis several good examples for natural photonic crystal,
Yes.
and here it's a butterfly, and also this other example. And I'm wondering, have you heard about scarab beetles?
Yes, I mean there is a lot of these beetles, like no, I might not have to. I had this article. There is this article that I've made a summary of all the natural.
Yeah, that is yeah, natural photonic waves. And as for artificial, it's the same effect as scarab beetles. It's a holosteric or pneumatic holosteric liquid crystal. At least that is exactly the same. But what I want to say is that it's only one, as a matter of fact, derivative. That's all.
And how do you make the
It's because it's anisotropic.
Yeah, but then
And
it's
with
okay,
anisotropy, and that is a helicoidal structure, and because
but then it's a very specific organic crystal then. Because it's yeah, I mean it's this
and the next was the page 47. You wrote that
30 or 40.
so 30. That fluctuation under 2% of the crystal periodicity close to the photonic band gap, even for crystals with high refractive index constant, destroying any photonic effects. Is it,
This is from calculations from the Korean book.
okay, and could you actually, well, a little bit comment with what it means?
But it means that you can have in your periodicity, let's say, you can have different effects. You can have, if you take a coloid, you can have difference in sizes, in the mode of the dispersity, and then you can have also difference in stacking. So let's say that you have ordered this one, and then these ones are ordered in this direction or whatever. So there is like a change in the periodicity itself. So let's say that here the periodicity is maybe A, and there the periodicity is A prime. And this change is less dangerous to the photonic effect than this change. So if you have a change in diameter here, and it is above 2%, then at least they state
Okay,
that
I
in the calculation.
so if, for example, we would have a photonic crystal, let's say with a periodicity 300 nanometers, and if a periodicity it will be more than plus minus well 2%, it's 6 nanometers. So if it will be 3 deviation of the pitch, it will be more than 6 nanometers. This means that we will not observe
No. What it says that the 2% is for the diameter. So if you have
okay, so it's for diameter, not for the pitch.
No, not for the periodicity change.
Okay.
So it says that the photonic crystal is less sensitive to this small change. You have the same bit, but you have changed a little bit the periodicity, and this is not as important as if you have a completely different change in. For instance, you order your so you still have order, but your bits are completely different in diameter. Then you kill completely, at least they say that you kill completely your photonic band. Whereas if you have the same bits, but you have a shift in the periodicity between the bits, you will still conserve your photonic band gap.
Okay, I see.
It is what they say.
Yeah,
what I understood what they say.
And also, you mentioned that the diffuse light is used to understand the sample difference. You diffuse light, you measure the diffuse scattering.
Yeah, the scattering, yes.
Yeah, and it's a help to understand the effects in
Yes, and I mean, it also depends on the geometry of what you observe, because
yeah,
since
and
it's
yeah,
clear
and
from-
I completely agree with you. But the question is how you actually make a difference between surface roughness and scattering that appears from
the wall.
volume.
It's actually quite difficult. It's actually very interesting. You can see the difference with that when you have the optical measurements before and after our meeting. So I think
And in page 141, at least
41. Well, this one is also. So this one is when you have a polystyrene and then you have added alumina. So this difference.
So and how you first a question, how you actually know if it's scattering because surface roughness or volume scattering?
Well, on this one, I cannot really. I mean, at the same time, I don't have any scatter reflection, so it's below the detection of my sample. So if I had like a huge surface scattering, I guess I should see it in reflection.
Actually, it would be my next question regarding that reflection. But in general case, how to you can make a difference? For instance, for transmit, you have a diffuse.
Here's the difference. Let's see. This is. Actually, I'm not entirely sure.
I think that to be sure that it's not a surface scattering, it's just necessary to read surface profile.
Yeah, well,
And be sure that it's a scattering, that it's a surface, not a white.
The surface profiling of the is not that easy. I mean, I have some measurement on the polystyrene, and it's a bit elastic. But from your question, I mean, this is also interesting because here we have before and after ion beam, and we will expect that ion beam will increase the surface roughness.
Yeah.
So we see in the B is the let's see. It's a diffuse over the total transmitted light, and it's at 800 nanometers, so it's far away from the photonic band gap, and the absorption of, well, there is no absorption. It's titania, so yeah, it's far away from the absorption of titania. And this is this is before ion milling, and this is after ion milling. And you see that after ion milling, it's increasing a lot. And if it would have, so I think that maybe that kind of shows that and I mean it's the same here. You can see that the diffuse over total is increasing after the deposition of titanium on the polystyrene.
Okay, so in your case, can you, for instance, state that it's scattering because defects? Or
No, I think it's more
the dominated or dominating was scattering.
No, I think it will be more the surface. In this case,
Okay.
Mostly in the case of the polystyrene because it's so.
Okay,
round.
so it's mostly surface.
Yes,
for
the opals.
Yeah.
For the opal, and I think for the inverse opal it will be more the defect that we will see because it's all completely open. It's a film that is open. So there is not much surface per se.
Okay, and could you again turn to that figure? It's
Well,
yeah. And I'm wondering, is it calculated or measured? Because it's
It's a bit. The thing is that I don't want to say it's measured because it's not the raw signal. It's I have applied several different.
So that is a theoretical data.
No, it's
So
measured, but
measured.
it's passed through some
Yeah, but
mathematical
it's
operation.
Okay, but that it's a measured. Is it not a direct method for obtaining this data? I mean, not what you obtained in the device.
Yeah, there is a difference between.
Is it not direct measure?
It's not full data. No.
Yeah, but it's measured.
It's still measured. Yeah.
And I also wondering why you have a quite good signal for diffuse transmission and well, zero for diffuse reflection.
Well, I think it's because my sample are so thick, so that in transmission it's.
But again, for transmission, if we can see for this data for diffuse, it's almost, well, in some cases even in 2 times higher than a specular signal, but it's no response in reflection. Are you sure that it's no, no error in experimental measurements? Or because if we see quite a good scattering for transmission.
Yeah, but
And almost nothing.
The thing is that there is not many manipulation that you can do. On
No,
so I'm not so sure.
I wish not say that you make some manipulation. I just wondering if you have checked this moment. Maybe something wrong with the calculation or not all factors have been taken.
Well, I don't know because the thing is that I mean this is an integrated sphere, and to get the diffuse reflection, you use this outlet.
A little bit strange that it's a good scattering measured for transmitted light and almost nothing for reflected light.
I'm not so sure. I mean, it's like like I say, there is not much manipulation that you can do. You can only remove part of the sphere or like change the place of your sample. And I have now I'm doing some measurements for someone else, and she told me to do this diffuse part. You basically have your sample for the reflection. I have the sample here, and I have the light cone that absorbs the specular light, and then you just remove this one to measure.
Okay, but
I don't know. Maybe I did something wrong.
oh, maybe not you. Maybe it's device itself. It's not perfectly calibrated, or I mean,
we have some trouble with the UV part, for instance. Because
if for instance, to use a reference sample with good scattering, good scattering for both for transmitted and reflected light, it will be the same, or it will be good?
I'm not very sure.
Okay.
Sorry, I have mostly measured my sample.
And in the page 65, yes. Equation 4.7 and equation 4.8.
Yes.
And both equations contain A.
Oh,
Yeah.
And
Okay.
it's because the thing is that there is the one who writes the equation is responsible for the instrument, and he had written the name of the different parts of the light or like measurement spectra that you need to put in the equation. They were quite long. And then my supervisor was like, no, you cannot have the long name in the equation. So then I renamed everything, and I didn't pay attention to the fact that.
Yeah, so it's not the same.
No, I'm sorry. This is a very, very bad mistake.
My last question, because I guess there's a lot of questions for you. It's factors K and M. Yeah, it's
which one I have here, please?
Yeah, K and I guess it's B M. It's correction factors.
Yes.
Yeah, and in 4.6 is M. And how you measured them?
Let's see. These
I found that
because there is one. Let's see. This one, I think it's me who measure it, the M1, and it's because we have on this integrating sphere,
yeah.
We have this reflector on the back. This spectral this white reflector, and we have something similar on the top, and something similar on this diffuse part. And the thing is that they didn't. The one who take care of the instrument. They made the calibration for the instrument with so for this big square, this the one that we use on one part of the instrument, but they didn't do it for the top sphere. So then since I use it for the diffuse measurements in reflection, I think that they explained me that I needed to do this like calibration factor. So this is basically, I got also quite confused on this one. But basically, when you have this integration sphere, you have the place where you put the sample in transmission here from the light source, and then you have a lot of entry ports. If you go from the top, you have an entry port here that you can open to look around and you see the detector. Then you have an entry port here, where you can put this spectranum, so this white coated square or cone, up to you. Then they have some other entrances that you don't open usually when you do measurements. And then they have another one here that is actually looking more like that. It's on the sphere with a little. And this one is also coated with a similar material, but this one, the one who are responsible for the instrument, they do the calibration because it gets dirty with time, so then they clean it, then they need to redo the calibration. So they measure this in an overall setup, and then they can get what they're supposed to measure, and then this correction factor wavelength by wavelength. But they didn't have for this one. So then what they tell me is that this one is quite similar to this one, and they don't clean it as often and so on, so that I could use this one to calibrate this one. Okay. So this, it has gotten quite complicated in the calibration between the calibration of the instrument, the calibration of like the different parts of the instrument. I myself got a bit confused. So this M is the correction that I am measuring for this one, and K I think is the correction for this one.
And I said that was the last question, but in a connection with the previous question regarding almost zero back scattering, you also made some theoretical calculation in this. Yes? Or no? I mean,
Which ones?
I just wanted to ask you, at least you mentioned, here it's mentioned about NIP library. It's open source library.
Yes, we made some calculation, but it's actually another student who did it. So I actually installed it on my computer, and then I got like other things to do. So I never did the calculation myself, but it's another student who did it. So
And
it's a collaboration.
This calculation is important to simulate scattering, back scattering, and
Yes, but
Freedom.
I think he did only he did only reflection and transmission for that. We didn't discuss much of the diffuse those
Yeah, but
categories.
it's possible. In principle, it's possible with this.
Then it could be interesting to check.
Kind of.
Indeed.
Yeah.
I wish.
Thank you very much.
Okay.
Okay, thank you, committee, for the questions, and then I will ask if there are more questions from the audience.
It sounds good. Ask question.
I have a question. Okay. About your thesis.
Okay, I know this type of question.
So,
That's quite two good ones. Middle? Where should I put myself?
on stage.
On the stage. Do you want the figure or on the stage where the stage is like okay?
So we're reading your thesis, and so we're wondering why are a Greek god and a mischievous big cat in your thesis? What do you think? Some typos, or you just have some fun in writing? There's some examples, or do you really have no idea?
Big cats and Greek gods. Where did you find that? Because I cited some, there is some animals, and when I was talking about vision, there is some lot of like Latin names, but I don't know what
Yeah, so you have the Morphodonis and the first Adonis. Morphosis, Adonis shape. If you saw
it's a pont. I said tiger, that's something. It's a panthère chameleon. Okay.
So yeah, there are some Greek god and Swedish speaker. And then during the work we have noticed we have some sample boxes. So what is the most important thing to have for the samples? Play with them or throw them on the table.
It's to play with them by throwing them on the table. I must say that I actually ask for specific samples because I'm a very clumsy person and I know about it. So even if I try, it's not that I'm clumsy, that I'm very energetic and I broke in my home. I broke a lot of glasses and stuff like that because I put them too fast or too strong and stuff. So now I have asked Andreas to order this sample. Actually, I have this sample order. These boxes, they are made, I think, mostly for people working in biology. But the interesting part is that there are some film that is like elastic. So then, when I show them during meetings, then we are passing the samples through because nothing can happen to them.
Yeah. Yeah, it's true. So in principle, all the three, but we remember C the most. So then you have visited Stockholm sometimes.
Yeah.
Why are you going to Stockholm so?
For all of the emotions.
Yeah.
Yeah. Actually, it was very nice. We have a colleague that is fan of opera, and we have organized an outing where almost all the colleagues went to the opera. It was quite nice.
So, and then you go on business trips. So when you go on business trips, what do you bring? Kind of a notebook, a business card, a big book, and a flush sheet, or the toothbrush.
I think it's a flush of the flush sheet. big book.
Yeah.
You don't really need the business character. I always forget them. And the two questions, you can always find it there. So,
Yeah. And then you also, when you go abroad, you experience some exotic food. When you go for a science festival in Finland, so which part of the food should you try to the taste, the menu, or the rye bread?
The menu is actually quite nice. It doesn't look like it. It's quite tasty. It's this. It's made from this tree, right? The sap of the tree, right? Or I say something silly. It is like this. Does anyone know what it's made of? Melas. Yeah, yeah. So it's from the sap of the tree. It's actually quite tasty.
Yeah.
But if you eat too much of it.
Yeah, it's too much. Yeah. So and then when you do your work, you have some equipment. Some are more important than others.
I eat the teapot. For sure.
Then you have written about different metal oxides in the band gaps in the thesis. So which little band
No.
do you think is your favorite? Is it the titanium? Is it the thing that is also in the thesis, the aluminum, or some of the marks that I didn't
You got it
find?
wrong. It's antiferrum. Look, it's right. It's aluminum is a Swedish metal bond. Antiferrum is Swedish.
Okay.
It's not.
So then you have seen, noticed you have a lot of different abilities and talents. So in your alternative career, what will fit you better? Film director, own a bakery, organize events, new board game festival.
I feel like I should explain a bit. Film director is because we made a film for, well, actually it's a friend that made the nice photocat setup. We made a film for East events, like they are doing now. The bakery is because I always supply cakes, partners, and when I don't, I go to them. Delphine, why you don't get cakes? Organizer of events is because I have been part of this association for PhD students where we had organized some outings and stuff. And then I'm quite a huge fan of board games, so I would not mind being a board game taster. I think on the bakery is an alternative. If I failed in science, it would be the bakery.
So, and then when you're not at work, out in the rural countryside, that is a good to learn, work out, the vampire outfit.
It's the vampire outfit.
It's chilly, but
yeah, it was actually quite cold.
yeah. Yeah, and then when you do the traditional styrofoam Marlboro, it's good to have some stuff on the boat. Because I heard so much it's good to have the paddles about the food on the boat.
We said D.
Yeah.
The interesting part here is that we have there is 3 people working in the division, and the one that is very, this is me, and this is a colleague, and he was very intent to join us for this, and then he looked at us after we had made all the inscriptions, and he said, "Is it important if I don't know how to swim?" And we were like, so he bravely come and trusted our design on the boat to not sink, and he didn't went to the water, and I was quite happy about it because
Yeah,
it's a bit frightening. Someone who does not know how to swim being on this kind of like little raft. Okay.
We finished our questions for us. Thank you.
Thank you.
This concludes then the public part of the presentation, and now the committee and your opponent and Lars, we will have the committee meeting. You have the Delphine will show you where to go.
Yeah, there will be a little bit of nice and a lot of waiting.
Take off the cube or wait.
Yeah.